The solar system is a vast and mysterious neighbourhood filled with wonders that stretch far beyond what our eyes can see. From scorching planets that dance close to the blazing sun to icy worlds drifting in the distant darkness, every corner of it tells a fascinating story about how our cosmic home came to be. Giant storms rage for centuries on Jupiter, rings made of shimmering ice circle Saturn, and tiny Pluto silently orbits on the edge of the unknown. Every planet, moon, and asteroid holds secrets waiting to be uncovered. Before we begin, subscribe to our channel and let us know in the comments below where in the world you're watching from. We're always eager to hear where our viewers are tuning in from. Around 4,600 billion years ago, long before Earth, the Moon, or any of the other planets existed, our solar system began as nothing more than a huge cloud of gas and dust drifting quietly through space. This cloud was made mostly of hydrogen and helium, the two lightest elements in the universe, along with traces of heavier elements like carbon, oxygen, silicon, and iron. Over millions of years, gravity began to pull the particles in this cloud close together. Slowly, the cloud started to collapse inward, spinning faster as it did, forming what scientists call a solar nebula, a swirling disk of gas and dust, with most of its material gathering toward the centre. At the heart of this spinning disk, pressure and temperature rose higher and higher. The more the gas and dust collapsed, the hotter the centre became, until nuclear fusion, the process that powers stars, finally began. At that moment, the Sun was born. The intense heat from the newborn Sun began to push away much of the remaining gas and dust, leaving behind a thinner disk around it. From this leftover material, the planets, moons, asteroids, and comets that make up the solar system slowly began to form. The solar system as we know it today includes the Sun, 8 planets, more than 200 known moons, millions of asteroids, countless comets, and unnumbered tiny particles called meteoroids. Together, all of these objects form a vast cosmic family bound together by gravity, each moving in its own path but all revolving around one central object, the Sun. The solar system is like a gigantic community of worlds, each with its own unique characteristics, but all sharing the same origin and all following the same central gravitational pull. The Sun is the true giant of this family. It contains an astonishing 99.8% of all the mass in the entire solar system. That means everything else, all the planets, moons, asteroids, and comets combined, make up less than 1% of the total. The Sun's immense gravity keeps everything in orbit, and its light and warmth make life possible on Earth. Without the Sun, there would be no energy, no warmth, and no movement, just a dark and frozen emptiness. The Sun itself is a star, classified as a G-type main sequence star, also known as a yellow dwarf. Even though the word dwarf might make it sound small, it is far from it. The Sun's diameter is about 1,400,000 kilometers, which is roughly 109 times the diameter of Earth. Its surface temperature is around 5,500 degrees Celsius, and its core can reach 15 million degrees. Deep inside, hydrogen atoms are constantly being fused together to form helium, releasing enormous amounts of energy. This energy travels outward through the layers of the Sun, and finally escapes into space as light and heat. Every second, the Sun releases more energy than humanity has used in all of recorded history. It shines with such brilliance that, even though it is about 150 million kilometers away, its light reaches Earth in just about 8 minutes and 20 seconds. This means that when you look up at the Sun, you're actually seeing it as it was 8 minutes and 20 seconds ago. That's how long light takes to travel from it to us. The sunlight that reaches Earth drives everything. It warms the planet, powers photosynthesis in plants, controls the weather, and even influences ocean currents and seasons. Every living thing on Earth depends directly or indirectly on this energy. Without the Sun, Earth would be a frozen, lifeless rock drifting in space. Beyond the Sun, the solar system stretches across a vast distance. The innermost planets, Mercury, Venus, Earth, and Mars, are called the terrestrial planets because they are rocky and solid. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are called gas giants or ice giants, depending on their composition. These outer worlds are much larger, but they are mostly made of gases like hydrogen, helium, methane, and ammonia, rather than rock. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky remnants left over from the early days of the solar system. These asteroids range from tiny pebbles to objects hundreds of kilometers across. They are pieces of material that never joined to form a planet, possibly because of Jupiter's strong gravity interfering with their formation. Beyond Neptune lies another region known as the Kuiper Belt, which contains many icy bodies, including Pluto, once considered the 9th planet, but now classified as a dwarf planet. Far beyond even the Kuiper Belt, there may exist the Oort cloud, a distant spherical shell of icy objects that surrounds the solar system. This region is thought to be the birthplace of long-period comets, those that take thousands or even millions of years to complete one orbit around the Sun. The solar system's size, if measured from the Sun to the outer edge of the Oort cloud, could stretch for more than a light year, though most of that space is almost completely empty. All the planets and other bodies in the solar system orbit the Sun because of its powerful gravity. The planets move in nearly circular paths called orbits, within a flat plane known as the ecliptic. The closer a planet is to the Sun, the faster it travels. Mercury, for example, takes only 88 Earth days to complete one orbit, while Neptune, the farthest planet, takes about 165 Earth years to make one journey around the Sun. This orderly system, with its predictable motions, is what has allowed humans to study, map, and understand the movements of the heavens. The solar system itself, however, is not standing still. It moves together as one giant system around the centre of the Milky Way galaxy. Our galaxy is a massive spiral made up of hundreds of billions of stars, and the Sun is just one of them. The solar system is located in one of the galaxy's spiral arms, called the Orion Arm or the local spur, about 27,000 light-years from the galactic centre. It takes the solar system roughly 225 million years to complete one orbit around the Milky Way. That means since its formation 4,600 billion years ago, it has made this galactic journey about 20 times. The Milky Way's centre is believed to host a supermassive black hole called Sagittarius A, which has a mass equivalent to about 4 million suns. The solar system's orbit around this enormous object keeps it travelling at an average speed of about 800,000 kilometers per hour, yet we don't feel this motion because everything, the Sun, the planets, and all of us on Earth, are moving together at the same speed. Back when the solar system was still forming, collisions were frequent. Tiny dust grains clumped together to form larger and larger particles. Over time, these grew into rocks, then into mountain-sized objects, and eventually into planetesimals, the building blocks of planets. When these planetesimals collided and merged under the force of gravity, they formed the planets we know today. Some of these collisions were so violent that they reshaped entire worlds. One of the most dramatic examples is thought to have happened early in Earth's history, when a Mars-sized body collided with the young Earth. The impact was so powerful that it blasted a huge amount of debris into orbit, which later gathered together to form the Moon. This theory, known as the giant impact hypothesis, explains why the Moon's composition is so similar to that of Earth's outer layers. Over billions of years, the solar system has changed dramatically. When it was young, leftover debris from planet formation frequently struck the planets and moons, leaving behind countless craters. Many of these can still be seen today on the surfaces of Mercury, the Moon, and Mars. But as time went on, most of the loose material was cleared away, and the solar system became more stable. The outer planets also played a major role in shaping the system's structure. Jupiter, with its immense gravity, helped to sweep up or fling away much of the debris that could have bombarded the inner planets. It also influenced the orbits of countless asteroids and comets. Saturn, Uranus, and Neptune did the same, creating a more orderly environment in which life could eventually arise on Earth. Even today, the solar system is still a dynamic place. Asteroids continue to orbit the Sun, sometimes colliding or breaking apart. Comets occasionally enter the inner solar system, developing bright tails as they approach the Sun, and their icy surfaces begin to vaporize. Meteoroids, which are much smaller rocks or dust particles, often fall into Earth's atmosphere, producing brief flashes of light known as meteors or shooting stars. The solar system is also surrounded by invisible forces and particles. The Sun constantly emits a stream of charged particles called the solar wind, which flows outward in all directions. This wind forms a vast bubble around the solar system known as the heliosphere. The boundary where the solar wind meets the interstellar medium, the thin gas and dust between the stars, is called the heliopause. Beyond this region, the influence of the Sun's magnetic field fades and the vastness of interstellar space begins. Two spacecraft, Voyager 1 and Voyager 2, launched in the year 1977, have travelled farther than any other human-made objects. They have now both passed beyond the heliosphere and entered interstellar space, carrying messages from Earth that may one day be found by another civilization. Their journey shows just how enormous the solar system truly is, and how small our world seems in comparison. The Sun, being a middle-aged star, has already lived through about half of its expected life. In roughly 5 billion years, it will exhaust its hydrogen fuel and begin to swell into a red giant. During that stage, it will expand so much that it may engulf Mercury, Venus, and possibly Earth. Later, it will shed its outer layers, leaving behind a dense core known as a white dwarf, a faint hot remnant about the size of Earth, but with half the Sun's mass. The surrounding gas will form a glowing shell called a planetary nebula, which will slowly fade into space. The Milky Way itself is an enormous spiral galaxy made up of hundreds of billions of stars, each with their own planetary systems and cosmic environments. The Sun, the heart of our solar system, orbits within one of the Milky Way's spiral arms, known as the Orion Arm or Orion Spur. This region lies between two much larger spiral arms, the Sagittarius Arm and the Perseus Arm. As the Sun travels through this region, it carries with it all 8 planets, their moons, and countless smaller objects. Though we often think of the planets as orbiting the Sun in a steady and unchanging path, in reality, they're all moving with the Sun through the galaxy at tremendous speeds, estimated at more than 200 kilometers every second. Despite this incredible speed, space is so vast that the journey around the Milky Way still takes hundreds of millions of years. Throughout this cosmic voyage, the solar system passes through different regions of interstellar space, where it may encounter varying densities of gas, dust, and cosmic radiation. These galactic environments can have subtle effects on the solar system itself. Some scientists believe that the solar system's position within the Milky Way may even influence the climate and evolution of life on Earth. For example, when the solar system moves through denser regions of the galaxy, or comes closer to massive clusters of stars, the increased exposure to cosmic rays and other energetic particles could affect Earth's atmosphere and even the rate of mutations in living organisms. Over the course of hundreds of millions of years, these changes could play a small but meaningful role in shaping the story of life on our planet. The 8 planets of the solar system accompany the Sun on this grand galactic journey. Each of these worlds is unique in its composition, size, and character. The 4 innermost planets, Mercury, Venus, Earth, and Mars, are known as terrestrial planets because they are made primarily of rock and metal. These planets are relatively small compared to the outer ones, but they have solid surfaces that can support mountains, valleys, and in Earth's case, life itself. Beyond Mars lie the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, known as the gas or ice giants. These worlds are enormous, mostly made of hydrogen, helium, or other lighter elements, and they lack the solid ground that defines the terrestrial planets. Together, these 8 planets form a system that reflects the diversity and complexity of the universe itself. Starting closest to the Sun, Mercury is the smallest of all the planets and the fastest to orbit. It completes a full circle around the Sun in just about 88 Earth days. Because it is so close to the Sun, Mercury experiences extreme temperatures. During the daytime, its surface can reach scorching levels, but at night, the lack of atmosphere allows the heat to escape, causing the temperature to drop to freezing levels. This constant cycle of heating and cooling creates a harsh and unwelcoming environment. Yet Mercury continues to be an object of fascination for scientists who study its surface features, craters, and mysterious magnetic field. Next is Venus, often referred to as Earth's sister planet because of its similar size and structure. However, the 2 worlds could not be more different in their conditions. Venus is covered by thick clouds made of sulfuric acid, and its atmosphere is rich in carbon dioxide, creating a powerful greenhouse effect. The heat trapped by this dense atmosphere raises the planet's surface temperature to levels hot enough to melt lead, making Venus the hottest planet in the solar system. The surface pressure is also incredibly high, more than 90 times that of Earth's, meaning that any spacecraft landing there would be quickly crushed by the weight of the atmosphere. Despite these challenges, Venus remains an important world of study because its conditions may hold clues to the future of Earth's own climate and the effects of atmospheric change. Third from the Sun is Earth, our home world, and the only known planet to support life. Earth's size, composition, and distance from the Sun create an ideal balance for liquid water to exist on its surface, which is one of the key ingredients for life. The atmosphere contains the right mixture of gases, mainly nitrogen and oxygen, to sustain living organisms and protect the surface from harmful radiation. Earth's surface is dynamic, constantly reshaped by plate tectonics, volcanic activity, and erosion. The presence of oceans, mountains, and continents gives it an extraordinary diversity of environments, from frozen poles to tropical rainforests. The planet's rotation and tilted axis also give rise to the cycle of day and night and the changing seasons. Earth's natural satellite, the Moon, plays a vital role as well by stabilizing the planet's rotation and influencing the tides of the oceans. Together, Earth and the Moon have formed a partnership that has lasted for billions of years, creating the perfect conditions for life to flourish. Beyond Earth lies Mars, often called the Red Planet because of its rusty iron-rich soil that gives it a reddish appearance. Mars is smaller than Earth, but larger than Mercury, and it has an atmosphere composed mostly of carbon dioxide. The planet's thin atmosphere means it cannot trap much heat, so temperatures on Mars are generally very cold. However, evidence from spacecraft and rovers has shown that Mars once had rivers, lakes, and perhaps even oceans of liquid water on its surface. Today, much of that water appears to be frozen in the planet's polar ice caps or buried beneath the ground. Scientists have long been fascinated by Mars because it is the most Earth-like planet in the solar system and a potential place where life might have once existed, or might exist in microbial form even today. The possibility of human exploration on Mars continues to capture the imagination of people everywhere. Past Mars, the solar system changes dramatically. The four outer planets, Jupiter, Saturn, Uranus, and Neptune, are enormous worlds compared to the inner planets. They are composed mainly of gases and ices, and do not have solid surfaces like Mercury, Venus, Earth, or Mars. These planets are surrounded by thick layers of atmosphere, powerful winds, and complex systems of moons and rings. They are sometimes called the giants of the solar system because of their immense size and mass. Jupiter, the largest of all, is truly colossal. Its diameter is more than 11 times that of Earth, and its mass is more than twice that of all the other planets combined. Jupiter is mostly made of hydrogen and helium, similar to the Sun, and it generates strong magnetic fields and intense radiation belts. One of Jupiter's most remarkable features is the Great Red Spot, a gigantic storm that has been raging for centuries and is large enough to swallow several Earths. Jupiter's system of moons is also astonishing. It has more than 90 known moons, including 4 large ones, Io, Europa, Ganymede, and Callisto, that were first discovered by Galileo Galilei in the early 17th century. Each of these moons is unique. Europa, for example, is covered in ice, and scientists believe there may be an ocean of liquid water beneath its frozen surface, making it a possible home for extraterrestrial life. Next is Saturn, famous for its stunning system of rings. These rings are made up of countless particles of ice and rock, ranging from tiny grains to massive chunks, all orbiting the planet in a delicate balance. Saturn itself is the second largest planet in the solar system, and like Jupiter, it is mostly composed of hydrogen and helium. The planet's atmosphere features swirling clouds and fierce storms, though they are more subtle than those on Jupiter. Saturn's largest moon, Titan, stands out as one of the most fascinating bodies in the solar system. Titan has a thick atmosphere and lakes made not of water, but of liquid methane and ethane. Scientists believe Titan's environment may resemble what Earth was like in its earliest days, long before life began. Beyond Saturn lies Uranus, a planet unlike any other. It is often called an ice giant because it contains large amounts of water, ammonia, and methane ices beneath its thick atmosphere. Uranus is unique because it rotates on its side with its axis tilted by about 98 degrees relative to its orbit. This means that for long periods one hemisphere faces the Sun while the other remains in darkness. The strange tilt may have been caused by a massive collision with another large body early in the planet's history. Uranus also has a faint system of rings and more than 24 moons. Its pale blue colour comes from methane gas in the atmosphere, which absorbs red light and reflects blue light back into space. Despite being far from the Sun, Uranus still plays an essential role in the structure of the outer solar system. The last of the 8 planets is Neptune, another ice giant and the most distant planet from the Sun. Neptune is similar in size and composition to Uranus, but is slightly denser and has more intense weather systems. The planet is known for its deep blue colour and powerful winds, which can reach speeds faster than any other in the solar system. Neptune's largest moon, Triton, orbits the planet in the opposite direction of Neptune's rotation, suggesting that it may once have been an independent object captured by the planet's gravity. Triton's surface features geysers that erupt with nitrogen gas, and its icy landscape continues to intrigue astronomers. Neptune also has faint rings and several smaller moons that add to the complexity of this distant world. Each of the 8 planets, from the rocky inner worlds to the massive outer giants, contributes to the balance and structure of the solar system. Their interactions through gravity shape the paths of countless asteroids and comets, influence the orbits of moons, and even affect the tilt and wobble of the Sun itself. The solar system is a living system in constant motion, where every object, no matter how small, plays a part in maintaining its harmony. As the solar system continues its long voyage around the Milky Way, it passes through regions of differing cosmic activity. Sometimes it moves through areas rich in interstellar dust, and at other times it enters relatively empty zones. Astronomers believe that these transitions may influence the rate of cometary activity in the solar system. For example, when the solar system travels through a dense region of the galaxy, the gravitational forces could disturb the Oort cloud, a vast spherical shell of icy bodies that surrounds the solar system at great distances. These disturbances may send comets hurtling inward toward the Sun, where they become visible in the night sky as bright, glowing visitors with long tails. The enormous scale of time involved in the solar system's galactic orbit also means that our place in the Milky Way has changed countless times since its formation. Since the solar system first formed about 4.5 billion years ago, it has completed around 20 galactic orbits. During that time, entire species of life have appeared and vanished, continents have drifted, and civilizations have risen and fallen, all while the Sun and its planets have continued their endless journey through the galaxy. The stars we see in the night sky are not fixed but constantly changing as both we and they move through the Milky Way. The constellations familiar to ancient people thousands of years ago looked different from those we see today, and will change again in the far future as the stars slowly shift positions. Even though the solar system is just one small part of the Milky Way, it represents a remarkable microcosm of the universe. Within its boundaries, there are all the elements that make up stars, planets, and living organisms. From the burning hydrogen in the Sun to the icy gases of Neptune, from the volcanic plains of Venus to the blue oceans of Earth, the solar system displays the full range of cosmic phenomena. Every planet tells a different chapter of the same great story, the story of how matter, energy, and gravity interact to create order and variety out of the chaos of the universe. Scientists continue to study the solar system, not only to understand our own origins, but also to learn about other planetary systems throughout the galaxy. The discovery of thousands of exoplanets, planets orbiting other stars, has shown that systems like ours are common in the Milky Way. Some of these distant worlds are massive gas giants orbiting close to their stars, while others may resemble Earth, potentially with oceans and atmospheres. By comparing them to our solar system, astronomers gain a deeper understanding of how planets form and evolve. The solar system serves as a model for exploring the greater universe, offering a living example of the processes that shape worlds everywhere. As it travels through the galaxy, the solar system carries the history of billions of years. The light from the Sun continues to shine across space, illuminating the paths of its planets as they circle it again and again. The gravitational bonds that hold everything together, between the Sun, the planets, the moons, and the smaller objects, keep the system in delicate balance as it moves through the immense expanse of the Milky Way. Though the distances and timescales are beyond human understanding, this slow and steady motion connects us to the galaxy around us. The Earth, along with every living being upon it, is part of a journey that began long before the first humans looked up at the stars and will continue long after the last traces of our civilization fade away. The solar system's orbit around the Milky Way is a journey of unimaginable duration, and yet in the grand timeline of the universe, it is only one cycle in a story that stretches far beyond the reach of time. The 8 planets, from Mercury's sun-scorched surface to Neptune's icy winds, continue to move in harmony, bound together by the sun's gravity and propelled forward through the galaxy. Every revolution of the planets, every year that passes on Earth, every sunrise and sunset is part of this greater movement through space. The solar system's voyage through the Milky Way is not merely a motion of planets and stars. It is the slow, unending rhythm of the cosmos itself, the heartbeat of a galaxy that carries our tiny world along its timeless path. The sun, that bright glowing sphere that lights up our skies each day, is far more than just a source of daylight and warmth. It is a massive, fiery ball of gas that has been burning for billions of years, shaping everything around it. Every planet, moon, comet and asteroid in the solar system depends on it for energy and stability. It has been shining for about 4,600,000,000 years, and even though it seems eternal to us, it is constantly changing and evolving deep within. The surface of the sun, which astronomers call the photosphere, has a temperature of about 5,500 degrees Celsius, which is around 9,932 degrees Fahrenheit. That is unimaginably hot, so hot that any solid or liquid substance would immediately vaporize upon coming anywhere near it. Yet, compared to the deeper layers of the sun, its surface is actually quite cool. Below the photosphere lies a realm of immense heat and pressure where atomic reactions constantly occur, keeping the sun alive and glowing. At the very center of the sun is its core, a place of staggering energy and power. The temperature there is about 15 million degrees Celsius, or roughly 27 million degrees Fahrenheit. Inside this core, the pressure is so intense that atoms of hydrogen are forced together to form helium through a process known as nuclear fusion. It is this reaction that releases the energy which eventually travels outward, reaching the surface and radiating across space to warm planets like Earth. Without this steady fusion, the sun would not shine, and life as we know it could not exist. The sun's energy takes an incredible journey before it reaches us. It begins deep within the core, where light and heat are produced. However, it can take thousands or even millions of years for that energy to make its way from the core to the outer surface, because it is absorbed and re-emitted countless times by the sun's dense layers of gas. By the time it escapes the surface and travels through space, it takes only about 8 minutes and 20 seconds for that sunlight to reach Earth. So, every time we feel the warmth of the sun on our skin, we are actually feeling light that began its journey millions of years ago. The sun's power is what keeps the entire solar system in order. Its gravity, an invisible force of attraction, holds all the planets in their orbits, from tiny Mercury close to the heat to icy Neptune far out in the cold darkness. Without this powerful gravitational pull, the planets would drift away into space, lost forever. The Sun is about 333,000 times more massive than Earth, and makes up nearly all the mass of the entire solar system. Because of this, its gravity dominates everything nearby, controlling the paths of planets, moons, and even the smallest dust particles that orbit within its reach. Although the Sun appears calm and steady from Earth, it is actually a very active and dynamic star. Its surface constantly changes, shaped by powerful magnetic forces that twist and tangle within it. Sometimes, dark patches appear on the surface. These are known as sunspots, regions that are cooler and darker than their surroundings. A sunspot may still be thousands of degrees hot, but compared to the surrounding areas, it is relatively cooler. Sunspots often appear in pairs or groups and can last for days, weeks, or even months before fading away. They are linked to the sun's magnetic activity, which waxes and wanes in cycles lasting about 11 years. When the magnetic energy stored within the sun becomes too strong, it can be suddenly released in massive bursts called solar flares. A solar flare is an intense explosion of energy that sends out radiation and particles into space. These bursts can be millions of times more powerful than a volcanic eruption on Earth. During a flare, the brightness of the sun's surface can increase dramatically in just seconds, and the shock waves of energy can travel across the solar system. When these high-energy particles reach Earth, they can disrupt communication systems, interfere with satellites, and even cause colourful auroras near the poles. Closely related to solar flares is another phenomenon called coronal mass ejection. Though it is not mentioned in the extract, it helps explain the Sun's activity. These are massive clouds of charged particles that the Sun hurls into space. When they collide with Earth's magnetic field, they can cause geomagnetic storms that make the northern and southern lights shine even more brilliantly across the skies. The Sun constantly releases a flow of charged particles known as the solar wind. This stream of electrons and protons moves outward through the solar system at tremendous speeds. The solar wind fills space with a bubble of particles and magnetic fields called the heliosphere, which acts as a protective shield, helping to block harmful cosmic rays from reaching the inner planets. However, when the solar wind interacts with Earth's magnetic field, it can create beautiful and colourful lights in the sky, the aurora borealis in the north and the aurora australis in the south. These glowing displays are reminders of how alive and active our Sun truly is. The process that powers the Sun, nuclear fusion, is one of nature's most incredible reactions. It begins with simple hydrogen atoms, which are the most common elements in the universe. Under the Sun's immense pressure and temperature, these hydrogen atoms combine to form helium. In doing so, a tiny part of their mass is converted into pure energy, according to Einstein's famous equation, E = mc2. This process releases enormous amounts of energy, enough to keep the Sun shining steadily for billions of years. Every second, the Sun converts around 600 million tons of hydrogen into helium, and about 4 million tons of that mass are turned into energy. Despite losing such an enormous amount of mass every second, the Sun is so large that this change is almost unnoticeable on human timescales. It has already been burning for about 4,600 million years, and it still has plenty of hydrogen left. But it will not last forever. Over time, as more hydrogen is turned into helium, the balance inside the Sun will gradually shift. The core will become denser and hotter, and the outer layers will expand outward. In roughly 5 billion years, the Sun will enter a new stage in its life and transform into what scientists call a red giant. When that happens, the Sun will swell to many times its current size, possibly large enough to engulf Mercury and Venus, and perhaps even Earth. Its colour will change from bright yellow to deep orange or red, and its outer layers will drift away into space, forming vast clouds of gas and dust. This stage will last for only a small fraction of its total lifetime, but it will mark a dramatic change in the solar system. The planets that survive will orbit a much larger, cooler and redder star than the one we know today. After spending millions of years as a red giant, the Sun will shed most of its outer layers, leaving behind only its hot, dense core. This remaining core will shrink into a small, faint object known as a white dwarf. A white dwarf is only about the size of Earth, but it will contain nearly all the mass that once made up the Sun. It will no longer produce energy through fusion, but it will continue to glow faintly for billions of years as it slowly cools down. Eventually, even that light will fade away into darkness. Though this future sounds distant and dramatic, it is a natural part of the life cycle of stars like our Sun. Stars are born, live for billions of years, and eventually die, giving birth to new stars and planets through the material they leave behind. The Sun is currently in the middle of its stable phase, called the main sequence, where it steadily burns hydrogen and maintains its balance between gravity pulling inward and pressure pushing outward. Even though it seems peaceful from our perspective on Earth, the Sun is constantly in motion. Gigantic waves of hot gas rise and fall on its surface, magnetic fields twist and snap, and enormous loops of plasma arch high into space. These loops can be larger than the Earth itself. The Sun also rotates, though not all parts of it move at the same speed. The equator spins faster than the poles, completing a rotation in about 25 Earth days at the equator and roughly 35 days at the poles. This uneven rotation contributes to the complex magnetic fields that create sunspots and solar flares. Scientists have studied the Sun using powerful telescopes, satellites, and space probes to better understand its behaviour. Observatories such as the Solar and Heliospheric Observatory, SOHO, and NASA's Parker Solar Probe have given us incredible images and data from close to the Sun. The Parker Solar Probe, launched in the 21st century, is the closest human-made object ever sent to the Sun, flying through the outer layers of its atmosphere, known as the corona. These missions have helped scientists understand how the Sun's energy moves outward, how solar wind is formed, and how space weather affects our planet. The Sun is not only important for warmth and light, it also influences the entire environment of our solar system. It affects the climates of planets, controls the movement of comets, and shapes the conditions that make life on Earth possible. Without the Sun, Earth would be a frozen, lifeless world drifting in darkness. Its light fuels photosynthesis in plants, providing food and oxygen for living beings. Its heat keeps the planet's water in liquid form and maintains the delicate balance needed for life to thrive. Throughout human history, people have always been fascinated by the Sun. Ancient civilizations worshipped it as a god or goddess, seeing it as a source of life and power. The Egyptians honored Ra, their sun god. The Greeks admired Helios, who they believed rode his chariot across the sky, and the Aztecs performed rituals to keep the sun strong and bright. Long before modern science, people understood that the sun was essential for survival, though they did not yet know the true nature of the burning sphere that ruled the skies. With the progress of science, especially during the last few centuries, humans have discovered more about how the sun truly works. Astronomers learned that it is a star, just like the countless others that fill the night sky. It may seem larger and brighter simply because it is much closer to Earth than any other star. In fact, light from the next nearest star takes over 4 years to reach us, while light from the sun arrives in just over 8 minutes. The sun's brilliance and stability have made life on Earth possible, but it also has the potential to cause disruptions. Solar storms, for instance, can affect technology in space and on the ground. When strong bursts of solar particles reach Earth, they can damage satellites, affect GPS systems, and even cause electrical blackouts. This is why scientists monitor solar activity carefully, studying sunspots and flares to predict when strong solar storms might occur. Another remarkable feature of the Sun is its magnetic field. This field extends far into space and plays a major role in shaping the solar wind and influencing planetary magnetospheres. On Earth, our magnetic field acts as a shield, protecting us from harmful solar radiation. Without it, the constant stream of particles from the Sun could strip away the atmosphere, just as it did on Mars billions of years ago. The study of the Sun's magnetism helps scientists understand not only our own planet, but also the histories of other worlds in the solar system. Despite its constant energy output, the Sun changes subtly over time. During the solar cycle, which lasts about 11 years, the number of sunspots increases and decreases. When activity peaks, the Sun's surface becomes more turbulent, with frequent flares and eruptions. This active period is called the solar maximum. When the cycle quiets down, it enters the solar minimum, with fewer sunspots and calmer conditions. These cycles can influence space weather and, to a lesser extent, Earth's climate. The light we receive from the Sun is not just one single colour or type of energy. It is made up of a wide range of wavelengths, from visible light to ultraviolet and infrared radiation. Ultraviolet light can be harmful in large amounts, which is why Earth's ozone layer is so important. It blocks much of the Sun's dangerous rays. Infrared light, on the other hand, carries heat and helps to warm the planet's surface. Scientists can learn about the Sun's composition and temperature by studying its light through a process called spectroscopy, which breaks down sunlight into its different colours to reveal the elements within it. The Sun is mostly made of hydrogen, about 74%, and helium, about 24%, with the remaining 2% made up of heavier elements such as oxygen, carbon, and iron. These elements, though small in proportion, play a key role in how energy moves inside the Sun. Over billions of years, as fusion continues, the balance of these elements will slowly shift. The core will grow richer in helium until the Sun eventually runs out of hydrogen fuel. That will mark the beginning of its transformation into a red giant. Even though the Sun's death as a white dwarf is inevitable, it will also give birth to new beginnings. The gas and dust expelled during its red giant phase will drift through space and may someday come together to form new stars and planets. In that sense, the Sun's life and eventual end are part of a greater cosmic cycle that continually renews the universe. Mercury stands as the smallest and closest planet to the blazing Sun, a tiny world racing around our star at incredible speed, locked in a cosmic dance of fire and ice. Although it is the nearest planet to the Sun, Mercury is not the hottest planet in the solar system. That title belongs to Venus. Yet Mercury is still an extraordinary place, full of extremes that make it one of the most fascinating and mysterious planets known to science. Every aspect of it, from its orbit its surface, its temperature, and even its strange day and night cycles, tells a story about how planets can exist and survive under some of the harshest conditions in the universe. Mercury circles the Sun at a distance of about 58 million kilometers, which is less than half the distance between the Earth and the Sun. Because it is so close, the Sun looks about 3 times larger in Mercury's sky than it does from Earth, and the sunlight there is more than 7 times stronger. This makes Mercury's environment extremely bright and hostile. When the Sun rises over Mercury's horizon, the surface bakes under intense radiation. But once the Sun sets, all that heat quickly disappears into the darkness of space, creating freezing conditions that are nearly unimaginable. During the daytime, the temperature on Mercury's surface can reach about 427 degrees Celsius, which is about 800 degrees Fahrenheit. That is hot enough to melt substances like lead or zinc. But at night, when the Sun moves below the horizon, the temperature drops sharply to around minus 173 degrees Celsius, which is about minus 280 degrees Fahrenheit. This is a temperature difference of about 600 degrees between day and night, something no other planet in our solar system experiences to this extent. This extreme difference happens because Mercury has no real atmosphere. On Earth, our thick atmosphere helps trap heat and spread it around the planet, which keeps temperatures from changing too much between day and night. Mercury, however, lacks this protective blanket. It has a very thin layer of particles called an exosphere, which is made up of tiny traces of oxygen, sodium, hydrogen, helium, and potassium. But this layer is so thin that it cannot trap any heat or provide any protection from the Sun's radiation. Without an atmosphere, Mercury's surface is exposed directly to the vacuum of space, which means heat escapes as soon as the Sun disappears. The absence of an atmosphere also means there is no wind, no rain, and no weather on Mercury. The planet's surface has remained nearly unchanged for billions of years. Craters of all shapes and sizes cover the landscape, reminders of ancient impacts from asteroids and comets that struck long ago. These craters have sharp edges, showing that they have not been worn down by erosion like those on Earth. One of the largest craters on Mercury is the Caloris Basin, which is about 1,500 kilometers across. It was formed billions of years ago when a massive asteroid collided with the planet, sending shock waves across its surface. The force of the impact was so strong that it caused strange ripples and ridges to appear on the opposite side of the planet. Mercury's surface also has large cliffs, known as scarps, which stretch for hundreds of kilometers and rise several kilometers high. Scientists believe these cliffs were formed as the planet's interior slowly cooled and shrank, causing the crust to wrinkle and crack. These features show that Mercury is a world that has been shaped by both violent impacts and slow geological changes over an immense amount of time. Even though Mercury has no air and experiences deadly temperatures, it still has some surprising secrets. For example, despite being so close to the Sun, there are places on Mercury that are permanently cold. At the planet's poles, there are craters so deep that sunlight never reaches their floors. These shadowed regions are some of the coldest places in the solar system, and spacecraft have detected bright reflections there that scientists believe come from frozen water, ice that has survived for billions of years, hidden away in eternal darkness. This discovery was astonishing because it proved that even a world scorched by the Sun can still hold pockets of ice, if the conditions are right. A day on Mercury is one of the strangest in the solar system. The planet spins very slowly on its axis, taking about 59 Earth days to complete one rotation. But because it also moves around the Sun so quickly, making one full orbit in only 88 Earth days, something unusual happens. From one sunrise to the next, a full day on Mercury actually lasts about 176 Earth days. That means if you stood on Mercury, you would see the Sun rise very slowly, climb halfway across the sky, stop, reverse direction for a while, and then continue on its way before setting again. This strange motion happens because of Mercury's unique combination of slow rotation and fast orbit. Mercury's year, the time it takes to go once around the Sun, is only 88 Earth days, making it the fastest planet in the solar system. It moves through space at nearly 47 kilometers per second, which is about 170,000 kilometers per hour. Because of this incredible speed, ancient astronomers gave it the name Mercury, after the Roman messenger god known for his swiftness. The Greeks also associated it with Hermes, the god of travel and speed. Even though they had no telescopes, early sky watchers could see Mercury with the naked eye, appearing as a small bright dot near the horizon just before sunrise or shortly after sunset. It never strays far from the sun in the sky, which is why it can only be seen during these times and never in the middle of the night. Over the centuries, Mercury remained one of the most difficult planets to study because of its closeness to the sun. Its bright glare made it hard to observe through telescopes. For a long time, scientists knew little about its surface or its true nature. That began to change in the 20th century, when space exploration made it possible to visit other worlds. The first spacecraft to fly past Mercury was Mariner 10, launched by NASA in the year 1973. Mariner 10 made 3 flybys of Mercury between 1974 and 1975, taking thousands of images that revealed a world covered in craters and scarps. It showed that Mercury's surface resembled that of the Moon, though it also had some unique features that made it distinct. Decades later, in the early 21st century, another spacecraft named Messenger was sent to Mercury. It was launched in the year 2004 and finally entered Mercury's orbit in 2011, becoming the first spacecraft ever to do so. For 4 years, Messenger studied the planet closely, mapping its surface in detail, measuring its magnetic field, and discovering chemical elements on its surface. It found evidence of ice in the polar craters and detected unusual materials that reflected light differently than expected. These findings completely transformed scientists' understanding of Mercury, showing that it was far more complex and active in its early history than previously thought. One of the most surprising discoveries about Mercury is that, despite being small, it has a magnetic field. This was unexpected because scientists once believed that only larger planets with molten metallic cores could generate such fields. Mercury's magnetic field is about 1% as strong as Earth's, but it still deflects some of the charged particles coming from the Sun. This means that Mercury's core must still be partly molten, even after billions of years. The presence of a magnetic field also suggests that the planet's interior is different from what scientists had imagined. It has an unusually large metallic core that makes up about 85% of its radius, surrounded by a thin rocky mantle and crust. Mercury's high density supports this idea. When compared to its small size, it is one of the densest planets in the solar system, second only to Earth. Scientists believe this is because, in its early days, Mercury might have been much larger, but a massive collision with another body stripped away much of its outer rocky material, leaving behind a dense metallic core. This violent past could explain many of Mercury's strange properties, such as its composition and magnetic field. Even though Mercury looks dead and silent today, it was once an active world. In its youth, volcanic activity reshaped large areas of its surface, covering old craters with smooth plains of solidified lava. Some of these lava plains are still visible today, stretching across the planet like vast frozen seas. The surface is also marked by long ridges and cliffs, formed as the interior cooled and shrank, compressing the crust over billions of years. Another mystery lies in the planet's colour. While it looks grey and dull from space, closer observation shows subtle shades of brown, yellow, and orange. These colours come from various minerals on its surface, such as magnesium and sulphur, which give Mercury its slightly mottled appearance. Its lack of atmosphere also means that the sky above Mercury is completely black, even during the daytime, allowing the sun to shine harshly against the dark background of space. The sun's power dominates every aspect of Mercury's environment. The sunlight is so intense that solar radiation and particles constantly strike the surface, knocking atoms off the rocks and sending them drifting into space. Some of these particles form a thin cloud around the planet, giving it a faint glow when viewed from certain angles. This constant bombardment also affects Mercury's exosphere, where atoms and molecules are continually lost and replaced. Because of its proximity to the Sun, Mercury experiences powerful gravitational forces. The Sun's pull causes the planet's orbit to be slightly oval-shaped rather than perfectly circular. This elliptical orbit means that Mercury's distance from the Sun changes as it travels. At its closest point, called perihelion, it is about 46 million kilometers away, while at its farthest point, called aphelion, it is about 70 million kilometers distant. This changing distance contributes to its temperature extremes and also creates a fascinating effect known as orbital precession. Over time, the point of Mercury's closest approach to the Sun slowly shifts around the Sun. This motion was one of the first observations that confirmed Einstein's theory of general relativity, showing that the curvature of spacetime caused by the Sun's mass affects Mercury's orbit. Mercury's appearance in the sky has long fascinated humanity. To ancient civilizations, it was one of the 5 visible planets that moved differently from the stars. Because it could be seen both in the morning and evening, some ancient astronomers thought it was 2 different objects, one seen before sunrise and another after sunset. The Babylonians called it Nabu, the messenger of the gods, while the Romans named it after their swift-footed god Mercury. The planet's rapid movement across the sky made it a symbol of speed, communication, and change. Even though Mercury is the smallest planet, it plays a big role in understanding how planets form and evolve. Its proximity to the Sun gives scientists valuable information about what conditions are like near a star. Studying Mercury helps astronomers learn how rocky planets like Earth, Venus, and Mars came to be, and what might happen to them as they age. In the darkness of space, Mercury's surface reflects only a small portion of sunlight, making it less bright than one might expect for such a sunlit world. Its surface reflects about 12% of the sunlight that hits it, similar to the reflectivity of the Moon's surface. Because of this, it appears as a dim, silvery disk when viewed through a telescope. Despite its brightness in the dawn or dusk sky, its surface itself is surprisingly dark. There are still many mysteries surrounding Mercury that scientists are trying to solve. One of them is why it has so much sulfur on its surface. Normally, such volatile elements would have evaporated away under the heat of the early sun, but Mercury somehow retained them. This might mean it formed farther from the Sun and later moved inward, or that its early environment was different from what scientists have imagined. Another mystery concerns the planet's magnetic field, which appears to be stronger in the northern hemisphere than in the southern one. This uneven distribution has puzzled researchers for years, suggesting that Mercury's core and magnetic field generation process are not symmetrical. Mercury's small size and lack of atmosphere also mean that it cannot hold onto gases or liquids for long. Any water vapour, carbon dioxide or nitrogen that might once have existed there quickly escaped into space. Yet the presence of ice at its poles raises interesting questions about how that water got there. Some scientists think it may have been delivered by comets or asteroids, while others suggest that hydrogen from the solar wind combined with oxygen in Mercury's surface materials to create water molecules that later froze in the polar shadows. The surface of Mercury also shows signs of what are called hollows, small bright depressions scattered across the terrain. These hollows appear to be unique to Mercury, and are thought to form when certain volatile materials near the surface vaporize into space, leaving behind small cavities. They give the planet's surface a pitted and uneven texture that makes it even more fascinating to study. Mercury's environment is also affected by constant bombardment from micrometeorites, tiny dust particles travelling through space. Since there is no atmosphere to burn them up, these particles strike the surface directly, slowly wearing it down and creating fine dust that covers the planet. This layer of dust, called regolith, gives Mercury its muted appearance and may have built up over billions of years. From the Earth, Mercury can be difficult to observe because it stays close to the Sun. The best times to see it are during what astronomers call greatest elongation, when the planet appears farthest from the Sun in the sky, either just before sunrise or just after sunset. During these times, Mercury can appear as a small, bright dot near the horizon, shining steadily against the fading light. The planet's motion is so fast that its position changes noticeably over a few days. Ancient astronomers were amazed by how quickly it moved, and even today, watching it glide across the twilight sky is a remarkable sight. Modern telescopes and spacecraft, however, have allowed us to see it in much greater detail, revealing the intricate patterns of craters, ridges and plains that mark its surface. In recent years, new missions have continued to explore Mercury. One of them is Bepi Colombo, a joint mission by the European Space Agency and the Japan Aerospace Exploration Agency. Launched in the year 2018, Bepi Colombo is on its long journey to Mercury, expected to arrive in the year 2026. Once it reaches orbit, it will study Mercury's magnetic field, surface composition, and interior structure in even greater detail than before. Mercury's orbit also causes it to move around the Sun much faster than any other planet. Since it is the closest planet to the Sun, the strong pull of the Sun's gravity makes Mercury race through its orbit in only about 88 Earth days. That means while we on Earth complete one full year, Mercury has already completed more than 4. but despite moving so quickly around the Sun, its rotation on its own axis is slow and unusual. Mercury turns very slowly, taking almost 59 Earth days to complete one full spin. This combination of a fast orbit and a slow spin causes strange effects on the planet's day and night cycle. On Mercury, one day from sunrise to sunrise lasts about 176 Earth days, meaning that a single day there is almost twice as long as its year. Because of its eccentric orbit and its slow rotation, the sunlight on Mercury's surface changes dramatically. At some points in its orbit, Mercury moves so close to the Sun that it receives an intense amount of solar energy. The sunlight there is more than 7 times stronger than what we receive on Earth. Yet because the planet has almost no atmosphere to trap heat, the temperatures on Mercury rise and fall in extreme ways. During the daytime, when the Sun shines directly on its surface, temperatures can climb to about 427 degrees Celsius, which is hot enough to melt some metals. But when night falls, the heat quickly escapes into space, and the temperature drops to around minus 173 degrees Celsius. This makes Mercury a world of extremes, a planet where fiery heat and freezing cold coexist side by side, depending on whether a place is in sunlight or shadow. The surface of Mercury tells a story of violence and change that has lasted for billions of years. When scientists first observed Mercury through telescopes, they noticed that its surface was covered with countless craters, similar to those on Earth's moon. These craters were formed long ago when large rocks and asteroids from space slammed into the planet. Because Mercury has no thick atmosphere to protect it, even small meteoroids can hit its surface directly. Over billions of years, these impacts have left scars all across the planet, creating deep craters, ridges, and vast plains. Some of these craters are enormous, hundreds of kilometers wide, while others are small and shallow. One of the largest and most striking impact sites on Mercury is called the Caloris Basin. This massive crater was formed by a huge asteroid collision billions of years ago. The impact was so powerful that it reshaped the planet's crust and caused strange patterns of cracks and cliffs to appear on the opposite side of Mercury. These cliffs, known as scarps, stretch for hundreds of kilometers and rise several kilometers high. They were formed as the planet cooled and its surface shrank over time, causing the crust to wrinkle and fold. This tells scientists that Mercury is not just a lifeless ball of rock, but a planet that has gone through enormous geological changes. The surface of Mercury is not just ancient, it is also extremely quiet. There are no winds, no rain, and no erosion like we have on Earth. Without an atmosphere to protect or change it, Mercury's surface has remained nearly the same for billions of years. The craters and plains that formed long ago are still there today, frozen in time. Scientists can look at them and read the story of Mercury's violent past like a history book written in stone. Every dent and ridge on its surface holds clues about how the early solar system looked and what kind of forces shaped the planets we see today. Another strange thing about Mercury is that it has a weak magnetic field. This is surprising, because scientists once believed that only planets with molten, moving cores could produce magnetic fields. Mercury is small and cool compared to Earth, so they expected its core to have solidified long ago. However, measurements taken by spacecraft revealed that Mercury still has a magnetic field, though it is much weaker than Earth's. The discovery suggests that Mercury's core may still be partially molten. The magnetic field, though weak, interacts with the solar wind, a constant stream of charged particles flowing from the Sun, and creates a small magnetosphere around the planet. This magnetosphere is much smaller than Earth's, but it still offers some protection from the intense solar radiation. Because Mercury is so close to the Sun, studying it from Earth has always been very difficult. The Sun's brightness hides Mercury from view most of the time, and even when it is visible, it appears as a tiny point of light near the horizon. For centuries, astronomers could only guess what the planet really looked like. That changed in the second half of the 20th century, when spacecraft began to visit the inner planets. The first mission to explore Mercury was NASA's Mariner 10, which flew by the planet 3 times in the mid-1970s. Mariner 10 sent back the first close-up images of Mercury's surface, revealing a world covered in craters, ridges, and plains. It also measured the planet's thin atmosphere, or exosphere, which is made up of tiny amounts of oxygen, sodium, hydrogen, helium, and potassium. After Mariner 10, no spacecraft visited Mercury for more than 30 years. It remained a distant mystery, a world too small and too close to the Sun for easy exploration. But in the early 21st century, NASA launched a new mission called MESSENGER, which stands for Mercury Surface, Space Environment, Geochemistry and Ranging. The spacecraft was launched in the year 2004 and finally entered orbit around Mercury in the year 2011, after making several flybys of Earth, Venus, and Mercury itself to slow down and match the planet's orbit. MESSENGER became the first spacecraft ever to orbit Mercury. For 4 years, from 2011 until 2015, it collected vast amounts of data about the planet's surface, magnetic field, and chemical composition. It took more than 200,000 detailed photographs, mapping nearly the entire surface of Mercury. These images revealed not only craters and plains, but also strange features called hollows, bright, shallow depressions that seem to form when volatile materials near the surface vaporize and escape into space. These hollows give parts of Mercury's surface a sparkling appearance, almost as if it were sprinkled with tiny mirrors reflecting sunlight. MESSENGER's discoveries completely changed what scientists thought they knew about Mercury. One of the most surprising findings was the presence of water ice at the planet's poles. For a long time, scientists had noticed that radar observations from Earth showed bright spots near Mercury's north and south poles. They suspected that these might be areas of ice, but many doubted it could exist so close to the Sun. However, MESSENGER confirmed that inside some of the deep craters near the poles, craters that never receive sunlight, there are thick layers of frozen water mixed with dark organic material. These craters are permanently shadowed because of Mercury's small tilt and slow rotation, meaning sunlight never reaches the bottom. In these places, the temperature stays cold enough for ice to survive for billions of years. This discovery was remarkable because it showed that even on the planet closest to the Sun, there can still be places cold enough to trap and preserve ice. The presence of ice on Mercury raised many new questions. Where did the water come from? Some scientists believe that it was delivered by comets and asteroids that struck Mercury long ago. Others think that water molecules could have been formed from interactions between hydrogen from the solar wind and oxygen in Mercury's surface minerals. However it got there, the discovery of ice in such an unlikely place showed that even the hottest and driest-looking planets might hide secrets deep in their shadows. MESSENGER also helped scientists understand more about Mercury's composition. It found that the planet has an unusually large iron core that makes up most of its volume. In fact, Mercury's core takes up about 85% of its radius, while Earth's core makes up only about half. This large core helps explain why Mercury is so dense despite being small. It also means that much of Mercury's surface crust is thinner than expected. Scientists think that in its early history, Mercury may have lost a lot of its outer rock layer because of massive collisions, or the intense heat of the young Sun. This left behind a world with a huge metal heart surrounded by a thin, rocky shell. The magnetic field detected by MESSENGER also gave new clues about Mercury's interior. Since magnetic fields are usually generated by the movement of molten metals inside a planet's core, the presence of a weak field on Mercury means that part of its core must still be liquid. This was surprising because Mercury is so small that it should have cooled down quickly after forming. To explain this, scientists suggested that the presence of lighter elements like sulfur might have kept the core partially molten even after billions of years. MESSENGER's measurements also revealed that Mercury's surface contains unexpected amounts of volatile elements like sulfur, sodium, and potassium. These are substances that usually evaporate easily under high heat, so their presence on Mercury suggests that the planet did not form under extremely hot conditions, as many scientists once thought. Instead, it may have formed farther from the Sun before moving inward to its current position. This idea challenges long-standing theories about how the inner planets formed and migrated in the early solar system. As MESSENGER continued its mission, it orbited closer and closer to Mercury's surface. It eventually ran out of fuel in the year 2015 and ended its mission by crashing into the planet. Before it did, it sent back one final burst of data that completed its detailed map of Mercury's surface. The information it provided continues to be studied by scientists today, revealing new insights about this mysterious world. Mercury's eccentric orbit not only shapes its climate and surface conditions, but also affects the way it interacts with the Sun's gravity. Because of its elongated orbit, Mercury's speed changes as it moves closer or farther from the Sun. When it is nearest to the Sun, at a point called perihelion, it travels much faster, while at its farthest point called aphelion it moves more slowly. This change in speed causes Mercury's orbit to shift slightly over time, a phenomenon known as the precession of the perihelion. For centuries, astronomers noticed that Mercury's orbit did not behave exactly as predicted by Newton's laws of gravity. The tiny difference puzzled scientists until the early 20th century, when Albert Einstein's theory of general relativity provided the answer. His equations showed that the curvature of space caused by the Sun's enormous mass slightly alters Mercury's orbit, making it advance over time. This discovery was one of the first major confirmations of Einstein's theory, showing that even a small planet like Mercury could help unlock deep truths about the universe. Mercury's orbit also gives it another strange feature. The Sun appears to move in an odd way in its sky. Because of the combination of its slow rotation and fast orbital motion, the Sun can appear to rise, stop, move backward for a while, and then continue rising again. This would be an extraordinary sight for anyone standing on Mercury's surface. From certain places, a person would see the Sun growing larger and smaller in the sky as the planet moves closer to and farther from it. Near perihelion, the Sun would look almost twice as large as it does when Mercury is at aphelion. Despite being so close to the Sun, Mercury has a surprisingly low brightness when seen from Earth. This is because its surface is dark and covered with a material that reflects little light. Scientists call this low reflectivity, low albedo. Mercury's surface is made mostly of silicate rocks mixed with dark minerals, giving it a dull, greyish-brown appearance. Unlike Venus, which is covered by thick clouds that reflect sunlight, Mercury's bare, rocky surface absorbs most of the sunlight that hits it. However, when it is seen through a telescope, especially when it is near its greatest elongation from the Sun, Mercury appears as a small but brilliant dot, a glimpse of a world bathed in harsh sunlight. Observing Mercury has always been a challenge for astronomers. Because it is never far from the Sun in the sky, it can only be seen shortly after sunset or just before sunrise. Even then, it stays close to the horizon and disappears quickly as the sky brightens. This is why Mercury was one of the least studied planets for so long. Ancient civilizations knew of its existence, of course. The Babylonians, Greeks and Romans all observed it and gave it names linked to their gods. The ancient Greeks called it Hermes, while the Romans later named it Mercury after their messenger god, because of its swift movement across the sky. Venus is the hottest planet in the entire solar system, a world that burns with a heat so great that even metals such as lead would melt on its surface. Its surface temperature is around 465 degrees Celsius, which is about 869 degrees Fahrenheit. This incredible heat makes Venus even hotter than Mercury, the planet that is much closer to the Sun. The reason for this extreme temperature is not how close it is to the Sun, but because of its thick and heavy atmosphere, which traps heat so effectively that almost none can escape. The planet has become a vast glowing furnace, wrapped in thick clouds that hide its surface from view. The atmosphere of Venus is made mostly of carbon dioxide, a gas that is also found on Earth but only in small amounts. On Venus, however, carbon dioxide makes up nearly the entire atmosphere. This gas is very good at trapping heat from sunlight, creating what scientists call a greenhouse effect. On Earth, the greenhouse effect helps keep the planet warm enough for life, but on Venus, the effect has gone far beyond anything we could survive. The Sun's rays pass through the thick clouds, strike the planet's surface, and are reflected back as heat. But the carbon dioxide holds the heat in, causing temperatures to rise higher and higher until the whole planet became a massive oven. Floating high above Venus's surface are clouds made of sulfuric acid. These clouds are thick, dense, and completely opaque, which means that even powerful telescopes cannot see the ground beneath them. The sulfuric acid droplets form because the atmosphere is full of sulfur and oxygen that combine under high pressure and heat. The clouds reflect most of the sunlight that hits them, which makes Venus shine brightly in our sky. To anyone looking from Earth, Venus appears as a brilliant white star, often visible in the early morning before sunrise or in the evening after sunset. Because of this, people long ago called it the morning star and the evening star. For thousands of years before humans knew it was a planet, Many cultures admired its beauty and built myths and stories around its bright light. The pressure at the surface of Venus is about 92 times greater than the pressure on Earth's surface. To imagine this, it would be like standing almost 1 kilometre underwater on Earth's ocean floor. Under such pressure, a human being or a spacecraft not built to withstand it would be crushed instantly. This enormous pressure comes from the thick layers of gas pressing down from the atmosphere above. The air on Venus is so heavy and dense that it would feel more like swimming in a hot, toxic ocean than standing in air. Because of this, the environment on Venus is one of the most hostile in the solar system, and any attempt to explore it directly has always been a great challenge. One of the most unusual things about Venus is the way it rotates. Unlike most of the other planets, which spin from west to east, Venus spins backward. This means that if you could stand on the planet's surface, the sun would rise in the west and set in the east, opposite from what we see on Earth. Scientists call this kind of movement retrograde rotation. No one knows for sure why Venus rotates this way, but many believe it might have been caused by a massive collision in the distant past, when a large object struck the young planet and slowed or reversed its spin. Venus also turns very slowly. In fact, one single day on Venus, which means one full rotation on its axis, takes about 243 Earth days. But one complete orbit around the Sun, which is a year for Venus, takes only about 225 Earth days. This means that a day on Venus is longer than its year. In simple terms, the planet spins so slowly that it finishes going around the Sun before it can complete a full rotation. This strange rhythm of time means that if someone could live on Venus, they would see the Sun rise and set only a few times during their entire year. Though in truth, no living creature could ever survive there because of the deadly heat and pressure. Venus is often called Earth's sister planet because it is almost the same size and has nearly the same mass as Earth. The two planets are also made mostly of rock and metal, and formed in similar ways around the same time, about 4.5 billion years ago. But despite these similarities, Venus and Earth could not be more different in their present state. While Earth has oceans, forests, and a mild climate that allows life to flourish, Venus has turned into a dry, burning world covered by thick clouds and endless plains of volcanic rock. Scientists believe that long ago, Venus might have been much more like Earth, perhaps even having shallow seas and a mild atmosphere. But as the planet grew hotter, its water slowly boiled away into space, and the carbon dioxide built up, leading to a runaway greenhouse effect that transformed it into the inferno we see today. Venus shines more brightly in the night sky than any other planet or star except the Moon. Its brightness comes from its thick clouds, which reflect about 70% of the sunlight that strikes them. Because of this high reflectivity, or albedo, Venus is easy to spot even with the naked eye. People in ancient times often used Venus to keep track of time, seasons, and directions. Civilizations such as the Babylonians, Mayans, and Greeks recorded its appearances and disappearances with great care, noticing how it alternated between being a morning and an evening object in the sky. The Mayans, for instance, had an entire calendar cycle based on Venus's movement, which they used for ceremonies and agriculture. Venus does not have any moons. Every other planet in the solar system except Mercury has at least one moon, but Venus travels alone. Scientists are not sure why this is so. Some believe that if Venus ever had moons, they might have been lost long ago, either crashing back into the planet or being pulled away by the sun's gravity. Others think that because of Venus's slow and unusual rotation, any moon that tried to form or be captured would eventually spiral inward and collide with the surface. This lack of moons makes Venus unique and adds to the many mysteries that surround it. After the success of the Soviet Venera missions, scientists around the world became more determined to study Venus in greater detail, even though the planet's environment was unlike anything else known in the solar system. Each mission added a little more to our understanding of this strange and fiery world. The data collected from the Venera landers and orbiters revealed a surface made mostly of volcanic plains, with mountains, craters, and vast highlands rising above the rest of the terrain. Some of these mountain ranges are taller than the highest peaks on Earth, showing that Venus once had an active geological past. What surprised many researchers was how smooth and young the surface appeared to be. Unlike the Moon or Mercury, which are covered with countless craters that have lasted for billions of years, Venus seemed to have far fewer craters, suggesting that its surface was reshaped relatively recently, possibly by widespread volcanic eruptions that covered older features. The idea of volcanoes on Venus quickly captured the interest of scientists. Many believed that the planet had once been covered by active volcanoes that poured lava across its plains, creating the dark, rocky landscape seen in the photographs. Later radar maps confirmed that Venus still has many volcanic structures, including enormous shield volcanoes and strange dome-like features called pancake domes, which are unlike anything found on Earth. Some of these volcanic formations stretch for hundreds of kilometers, forming immense lava flows that appear frozen in time. Though no direct eruption has been observed, certain temperature changes and gas variations detected in the atmosphere suggest that Venus may still be volcanically active today. If this is true, it would mean that beneath its thick clouds, the planet continues to reshape itself with hidden bursts of fiery energy. The radar mapping of Venus was one of the greatest achievements of space exploration. Since the planet's thick clouds prevent ordinary cameras from seeing its surface, scientists used radar waves, which can pass through the clouds and bounce back from the ground. These radar signals created detailed maps showing mountains, valleys, and plains in high resolution. The American spacecraft Magellan, launched by NASA in the year 1989, played a major role in this discovery. Orbiting Venus for several years, it mapped over 98% of the planet's surface. The images showed a world that was both beautiful and hostile, a place of massive volcanoes, winding canyons, and enormous impact craters scattered across a dry, cracked crust. Some regions showed signs of once flowing lava that had hardened into strange patterns, while others were covered by smooth plains that might have formed from ancient volcanic floods. Even though Venus has no water, scientists noticed that many of its features look similar to river valleys and drainage channels. These may have been formed not by water, but by the movement of lava or by gases escaping from the interior of the planet. The surface also has bright streaks and dark patches, thought to be caused by different kinds of minerals reacting with the sulfuric atmosphere. The overall colour of the surface, based on images and radar data, is a yellowish-brown tone, as if the entire planet were baked by eternal sunlight. However, sunlight barely reaches the surface because the thick clouds scatter and absorb most of it. If you stood on Venus, the sky would look dim and orange, and the sun would appear only as a faint glow through the heavy haze. The atmosphere of Venus is a thick, churning sea of carbon dioxide, nitrogen, and sulfur compounds, with winds that blow at tremendous speeds high above the surface. These winds can reach up to 360 kilometers per hour, circling the planet in just a few days. Strangely, while the upper atmosphere moves so fast, the surface winds crawl slowly, only a few kilometers per hour. This difference means that the upper layers of the atmosphere are in a constant state of violent motion, while the lower part remains dense and almost still. The clouds are made mostly of sulfuric acid droplets, and they form several distinct layers that extend for tens of kilometers in thickness. These clouds are responsible for the planet's bright appearance, as they reflect sunlight very effectively, but they also make Venus a dark and deadly place below. Early astronomers believed that Venus might be covered with thick clouds of water vapour, perhaps hiding a lush tropical world beneath. For a long time, people imagined that beneath its dense atmosphere there could be jungles, swamps, or even oceans. This idea lasted well into the 19th and early 20th centuries, mainly because the bright clouds of Venus looked so similar to the weather systems of Earth. Since the clouds reflected so much light, many thought they must be made of water, and that Venus might have a humid, steamy climate full of life. Some writers of science fiction even pictured Venus as a planet of endless rainforests, or mysterious oceans filled with alien creatures. It was only after the first spacecraft sent back data in the mid-20th century that these dreams vanished, replaced by the harsh reality of an unbearably hot, dry and poisonous world. The earliest spacecraft to visit Venus were flyby missions, which passed close to the planet to collect information about its atmosphere, temperature, and magnetic field. In the early 1960s, NASA's Mariner 2 became the first successful mission to another planet. It flew past Venus in the year 1962 and confirmed that the planet's surface was extremely hot, far hotter than anyone had expected. This single discovery ended all hopes that Venus might be Earth's twin in terms of habitability. Later missions, such as Mariner 5 and Mariner 10, added to the data, measuring its pressure, composition, and the lack of a strong magnetic field. These missions painted a clear picture. Venus was not a water-rich paradise, but a dry world shrouded in acid and heat. The lack of a strong magnetic field on Venus was another important finding. Earth's magnetic field protects it from solar wind, the stream of charged particles coming from the Sun. Without such protection, these particles can strip away a planet's atmosphere over time. Venus, however, manages to hold on to its dense atmosphere, despite not having a powerful magnetic shield. Scientists believe this happens because Venus's atmosphere is so thick that the upper layers act like a protective barrier, deflecting much of the solar wind. Still, this absence of a strong magnetic field also means that Venus's surface is exposed to a constant bombardment of high-energy particles, making it even more hostile to any form of life. The Soviet Union took the lead in exploring Venus more closely, sending a long series of spacecraft known as Venera, meaning Venus in Russian. Venera 7, launched in the year 1970, achieved a historic milestone by becoming the first spacecraft ever to successfully land on another planet and transmit data back to Earth. Though it survived for only 23 minutes before the crushing pressure and heat destroyed it, those 23 minutes marked a turning point in planetary exploration. The data it sent confirmed the extreme surface temperature and pressure, proving once and for all that Venus was a world of unimaginable intensity. Later, Venera missions became more advanced, carrying better cameras and scientific instruments. Venera 9 and Venera 10, which landed in the year 1975, sent back the first black and white images from the surface of Venus. The pictures showed flat rocks and dusty ground stretching to the horizon under a hazy yellow sky. Venera 13 and Venera 14, launched in the early 1980s, went even further. They took colour photographs and analysed the composition of the rocks, finding that the surface was made mostly of basalt, a kind of volcanic rock similar to what is found in lava flows on Earth. These missions also recorded the sounds of the wind, a faint but steady whisper in the thick air, which gave scientists a deeper sense of what it would be like to stand on that alien world, even if no human ever could. The success of the Soviet missions was followed by renewed efforts from other countries. NASA's Pioneer Venus mission in the late 1970s sent orbiters and probes to study the atmosphere in more detail. These spacecraft discovered that Venus's upper atmosphere contained several layers of clouds, each made of different materials. They also found lightning and thunder-like phenomena, suggesting that electrical storms might exist within the thick clouds. The atmosphere turned out to be full of strange behaviours, fast-moving winds, spinning patterns, and waves that wrapped around the entire planet. In some ways, Venus's atmosphere acts like a giant machine, driven by the sun's energy and the planet's slow rotation. Understanding this chaotic system helps scientists learn more about how atmospheres work on other planets, and even on Earth. Venus's rotation remains one of its most puzzling mysteries. Because it turns so slowly, one side of the planet spends an incredibly long time facing the sun, while the other side remains in darkness for months. Yet the temperature on both sides stays nearly the same. This happens because the thick atmosphere constantly moves heat around the planet, spreading it evenly. This effect, called global circulation, means there is almost no temperature difference between day and night on Venus. The winds high above the surface move so quickly that they circle the planet in just about 4 Earth days, far faster than the planet itself rotates. This phenomenon, known as superrotation, is one of the most unusual features in the solar system, and scientists are still trying to fully understand what causes it. The surface of Venus is divided into several major regions. There are vast lowland plains that cover most of the planet, large highland areas that rise thousands of meters above the plains, and deep valleys and craters formed by ancient impacts. One of the most striking highlands is called Ishtar Terra, located near the planet's north pole. It contains a massive mountain range known as Maxwell Montes, which is the tallest on Venus, rising about 11 kilometers above the average surface level, even taller than Mount Everest on Earth. Another highland region, Aphrodite Terra, stretches across the equator and is as large as Africa. These names, drawn from mythological goddesses, reflect the long-standing tradition of naming Venusian features after women, in honour of the planet's association with the goddess of beauty and love. Many of the volcanic features on Venus are unlike anything found on Earth. There are circular structures called corona, which are large, ring-like formations thought to be caused by hot material pushing up from inside the planet and then collapsing back down. Some coronae are hundreds of kilometers across, surrounded by cracks and ridges that mark where the surface is stretched and bent. These structures suggest that Venus's crust is constantly under pressure from heat and movement within its interior. Scientists believe that instead of having separate moving plates like Earth does, Venus's entire crust might act as one giant plate that occasionally melts and reforms due to heat buildup. This process could explain why the surface appears relatively young, with few craters compared to other rocky planets. Among all the planets that circle the Sun, Earth stands alone as the only known world that shelters life. It is a planet filled with forests that breathe, oceans that move endlessly, mountains that rise high into the sky, and deserts that stretch into shimmering horizons. It is a place where water flows, air swirls, and life grows in countless forms, from the smallest microorganism to the largest whale. Every part of Earth, from its deep interior to its outer atmosphere, plays a vital role in maintaining the balance that allows life to exist. It is not merely a rock spinning in space, it is a dynamic, living planet that has evolved for billions of years to become what it is today. Around 71% of Earth's surface is covered by water, making it a true blue planet when seen from space. This immense amount of water exists in oceans, rivers, lakes, ice caps, and even underground reserves. The oceans, which make up most of this water, are like the lungs and heart of the planet. They regulate temperature, produce much of the oxygen that living things breathe, and provide a home for millions of species. From the shallow coral reefs near coastlines to the mysterious deep-sea trenches where sunlight never reaches, water gives life in ways that scientists are still uncovering. The remaining 29% of the surface is land, where mountains, plains, forests and deserts spread across vast continents and islands. These landscapes have been shaped over millions of years by wind, water and the movement of the planet's crust. Earth's one and only natural satellite, the Moon, has always been a constant companion in the night sky. It orbits Earth at an average distance of about 384,000 kilometers and affects our world in many ways. The most visible effect of the Moon is the rise and fall of ocean tides. Its gravitational pull gently moves the seas back and forth, shaping coastlines and influencing marine life. The Moon also helps to stabilize Earth's tilt, keeping our climate from changing too wildly over long periods. Without the Moon, our nights would be much darker, the tides would be weaker, and the planet's rotation might wobble in unpredictable ways that could make life far more difficult. The Moon's phases, from crescent to full, have guided human cultures for thousands of years, marking time, festivals, and harvests. Even though it is lifeless and covered in dust, its silent presence connects us to the larger rhythm of the cosmos. Surrounding our planet is a thin but crucial layer of gases known as the atmosphere. This invisible blanket makes life possible. About 78% of Earth's atmosphere is nitrogen, a gas that does not react easily but is vital for life because it forms the building blocks of proteins and DNA. Around 21% of the atmosphere is oxygen, the gas that humans and most animals need to breathe. The small remaining fraction includes argon, carbon dioxide, and trace gases that, though present in tiny amounts, have huge effects on the climate and environment. For example, carbon dioxide helps trap heat from the sun, keeping the planet warm enough for liquid water to exist. Water vapor in the air forms clouds, rain, and snow, creating the endless cycle of weather that shapes every living environment on Earth. The atmosphere also shields us from dangerous radiation and meteoroids. As the sun sends out energy and charged particles, the upper layers of the atmosphere absorb and scatter most of this harmful radiation. When space rocks fall toward Earth, they usually burn up in the atmosphere, appearing as bright streaks of light called meteors. Without this protective shell of air, life could not survive the harshness of space. The sky that appears so calm from the ground is actually a busy protective barrier, constantly interacting with sunlight, magnetic forces, and the planet's surface. Earth's rotation axis is tilted at about 23.5 degrees from the vertical, and this tilt is the reason we experience seasons. As the planet travels around the sun once every year, different parts of Earth receive varying amounts of sunlight. When the northern hemisphere leans toward the sun, it experiences summer, with longer days and warmer temperatures. At the same time, the southern hemisphere tilts away and experiences winter. 6 months later, the situation reverses. This gentle tilt creates the rhythm of spring, summer, autumn, and winter that shapes ecosystems and agriculture around the world. Without it, there would be no change of seasons, and the planet would have a much more uniform but less diverse climate. The tilt also affects the migration of animals, the blooming of plants, and even human traditions that have developed around the yearly cycle of light and warmth. Deep within the planet lies another source of wonder, the magnetic field. Generated by the movement of molten iron in Earth's outer core, this invisible shield protects the planet from solar wind, a constant stream of charged particles that flows outward from the sun. If not for the magnetic field, the solar wind could gradually strip away our atmosphere, leaving Earth barren and lifeless like Mars. The magnetic field also guides the migration of certain animals, such as birds and sea turtles, which can sense the magnetic lines that encircle the planet. Sometimes, when solar particles collide with this magnetic field near the poles, they create breathtaking displays of coloured light in the sky known as auroras. These glowing curtains of green, red and purple light are not only beautiful, but also visible reminders of the planet's natural defences at work. The structure of Earth beneath our feet is as complex as its surface. The planet is made up of several layers, each with different properties. At the centre lies the inner core, a solid sphere mainly made of iron and nickel. Temperatures here are believed to reach around 6,000 degrees Celsius, nearly as hot as the surface of the Sun. Despite the heat, the immense pressure at the core keeps it solid. Surrounding the inner core is the outer core, a layer of liquid metal that flows slowly around the solid centre. This movement of molten iron creates electric currents, which in turn generate the magnetic field that encircles the planet. Above the core lies the mantle, a thick layer of hot rock that moves slowly over time. This movement drives the shifting of the continents and the rise of mountains. Finally, there is the crust, the thin, solid outer shell on which all living things exist. Though it feels stable beneath our feet, the crust is constantly changing, shaped by forces deep within. Earth's crust is broken into large pieces known as tectonic plates, and their slow movement has been shaping the planet's surface for hundreds of millions of years. These plates float on the semi-fluid mantle beneath them and move just a few centimeters each year, about the same rate at which fingernails grow. When plates move apart, molten rock from the mantle rises to form new crust, often creating mid-ocean ridges. When they collide, one plate may slide beneath another, forming deep ocean trenches or pushing up mountain ranges like the Himalayas. The movement of plates also causes earthquakes and volcanic eruptions. These events can be destructive, yet they are also part of the natural process that renews the planet's surface. Over long periods, tectonic activity has created continents, islands, and entire ocean basins. It has also recycled elements essential for life, bringing nutrients from deep within the Earth to the surface. Among the many wonders on the surface of our world stands Mount Everest, the highest point on Earth, reaching about 8,849 meters above sea level. Located in the Himalayas between Nepal and Tibet, it has long captured the human imagination. For climbers, it represents one of the greatest challenges, and for geologists, it is a reminder of the power of tectonic forces. The mountain continues to rise slowly each year as the Indian plate pushes into the Eurasian plate. The air at its summit is extremely thin, with only about 1/3 of the oxygen available at sea level. The conditions are harsh, yet the region around the mountain supports a variety of life forms, from snow leopards and yaks to rare high-altitude plants. Everest is not just a peak of rock and ice, but a symbol of Earth's vastness and diversity. In contrast to this towering mountain, the planet's lowest point lies deep beneath the Pacific Ocean, in the Mariana Trench. The deepest part of this trench, known as the Challenger Deep, reaches about 10,924 meters below sea level. At this depth, the pressure is more than 1,000 times that of the surface, and sunlight never penetrates. Yet even here, in total darkness, life exists. Strange and resilient creatures have adapted to the extreme conditions, living off chemical reactions instead of sunlight. The existence of life in such places shows how adaptable living organisms can be, and how little we still know about the full range of life on Earth. The Mariana Trench is a reminder that our planet still holds mysteries, even in its most remote and hostile environments. The surface of Earth is constantly changing due to natural processes such as erosion, volcanic activity, and the movement of water. Rivers carve valleys, glaciers grind down mountains, and winds shape deserts into vast seas of sand. Over time, these forces create and erase landscapes, showing that even the most solid ground is never truly still. Volcanoes, for instance, can form new islands overnight as molten rock rises from below and cools in the ocean. One example of this ongoing change is the Hawaiian Islands, which are formed by volcanic activity in the middle of the Pacific Plate. While some volcanoes remain active and dangerous, their eruptions also enrich the soil, creating fertile lands that support lush vegetation once the lava cools. Water, the most abundant and life-giving substance on Earth, also plays a major role in shaping the planet. Rain and rivers wear away rocks, carrying minerals to the oceans and creating fertile valleys where civilizations have flourished for thousands of years. The water cycle, evaporation, condensation, and precipitation, keeps the planet's climate balanced. Every drop of water that falls as rain or flows in rivers has been part of this cycle for millions of years, evaporating into clouds and falling again countless times. Even ice plays a role, forming glaciers that store vast amounts of fresh water and reflect sunlight, helping to regulate global temperature. Life on Earth exists in nearly every corner, from the icy poles to the burning deserts, from the mountain peaks to the ocean depths. Some organisms live in boiling springs, others inside rocks, and some even survive in the frozen tundra where temperatures fall far below zero. This incredible variety of life, plants, animals, fungi, and microorganisms, forms the biosphere, a delicate and interconnected web. Every species, no matter how small, plays a role in maintaining balance. Plants produce oxygen, animals help pollinate and spread seeds, and decomposers recycle nutrients back into the soil. Together, they create the conditions that allow life to continue generation after generation. Earth's climate and weather are also part of this complex system. Winds distribute heat and moisture, ocean currents move warm and cold water across the globe, and the tilt and orbit of the planet influence temperature patterns over long periods. Sometimes, natural changes like volcanic eruptions or shifts in ocean circulation can alter the climate for years or even centuries. Over geological time, Earth has experienced ice ages and warm periods, but life has always adapted, changing and evolving with the planet. Human activity, however, is now affecting the atmosphere and climate at an unprecedented rate, showing how deeply interconnected all aspects of the Earth system truly are. The story of Earth is also a story of time. Scientists estimate that the planet formed around 4.5 billion years ago from dust and gas left over after the birth of the Sun. In its early years, Earth was a hot, hostile world, constantly bombarded by asteroids and volcanic eruptions. Over millions of years it cooled, water condensed to form oceans, and simple life began to appear. From single-celled organisms, life evolved into more complex forms, eventually leading to the vast diversity we see today. Continents drifted, mountains rose and eroded, and climates changed many times, but life always found a way to adapt. Earth's balance between its atmosphere, magnetic field, water, and geological activity is what sets it apart from every other planet known so far. Each part supports the others in a web of connections that keeps the planet alive and habitable. The air protects the surface from radiation and provides gases for breathing and growth. The water regulates temperature and allows chemical reactions necessary for life. The magnetic field shields the atmosphere from the solar wind. The rotation and tilt of the planet create patterns of light and darkness that guide the rhythms of all living things. Even the smallest changes in one of these systems can affect the others. A rise in temperature can melt ice, raising sea levels and altering ocean currents. Volcanic eruptions can fill the atmosphere with ash, blocking sunlight and cooling the planet. Plants and microorganisms can change the composition of the air, while tectonic movements can reshape continents and redirect ocean flow. This constant exchange of energy and matter is what makes Earth not just a planet but a living system, always moving, breathing, and changing. The relationship between Earth and the Sun is another essential part of this balance. The planet orbits the Sun at a distance of about 150 million kilometers, a position often called the Goldilocks zone, because it is neither too hot nor too cold for liquid water to exist. This distance allows for a climate that can support oceans, weather, and life. If Earth were slightly closer, the water might evaporate. If it were farther away, it might freeze. The Sun's light and warmth drive the weather, power photosynthesis in plants, and provide the energy that fuels almost every process on the planet. Looking at Earth from space, astronauts often describe how fragile and beautiful it appears. A blue and white sphere floating in the darkness, with swirling clouds and shining oceans. From that distant view, the boundaries between continents and nations vanish, revealing the planet as a single, interconnected home shared by all forms of life. The water that covers most of its surface, the air that fills its atmosphere, and the land that stretches across its surface all work together to sustain this remarkable world. Over billions of years, Earth has gone through endless changes. Continents have drifted apart, mountains have formed and crumbled, and entire species have come and gone. Yet the planet continues to support life in all its diversity. Its ability to recover and renew itself shows how deeply it is shaped by both stability and change. From the deep oceans to the highest peaks, from the frozen poles to the warm equator, every part of Earth tells a piece of the story of life's long journey across time. The oceans that cover most of the planet are like vast laboratories of evolution. In their depths, life first began, and even today, the majority of Earth's living organisms remain hidden beneath the waves. Coral reefs teem with colourful fish and invertebrates. Kelp forests sway with the movement of the tide, and whales travel across entire oceans following ancient routes. The diversity found in the sea mirrors the complexity of life on land, showing that every drop of water contributes to the larger story of the planet. On land, forests cover large areas, acting as the lungs of the Earth. They absorb carbon dioxide and release oxygen, helping to regulate the planet's climate. Rainforests, in particular, hold an astonishing number of species, many of which scientists have not yet discovered. Deserts, though dry and seemingly lifeless, are home to plants and animals that have adapted to survive with little water. Grasslands stretch across continents, providing food for countless grazing animals, while tundra regions near the poles support hardy mosses, lichens, and migrating birds. Together, these ecosystems form the living surface of Earth, each with its own beauty and importance. The Moon's influence extends beyond tides and stability. It also connects humanity to the wider universe. The light it reflects has inspired poetry, science, and exploration. When humans first walked on the Moon in 1969, it was not just a technological achievement, but a moment that deepened our understanding of Earth itself. From the lunar surface, astronauts saw the planet rising above the horizon, a small, bright sphere filled with colour and life. That sight reminded humanity of how rare and precious our home truly is. The deep structure of the planet, the invisible forces of magnetism and gravity, the endless motion of water and air, and the fragile layer of life on the surface. All these parts together make Earth a world unlike any other we have found. Every earthquake, every wave, every gust of wind, and every drop of rain is part of the same intricate system that has worked for billions of years to sustain the living world. The journey of Earth continues every day as it spins on its axis, tilts toward and away from the Sun, and drifts silently through the vastness of space, carrying with it the only known spark of life in the entire universe. Mars, often called the Red Planet, stands as one of the most fascinating worlds in our solar system. When people look up at the night sky, Mars appears as a glowing reddish dot that has inspired curiosity, legends, and scientific exploration for thousands of years. Its striking colour comes from a simple yet powerful element, iron oxide, the same substance that causes rust on Earth. The planet's surface is covered in fine dust rich in this reddish material, giving it its unforgettable hue. This rusty coating reflects sunlight in a way that makes Mars glow with a reddish tint, which is visible even to the naked eye from Earth. It is this distinctive colour that earned Mars its famous nickname and set it apart from all the other planets orbiting the Sun. The ancient civilizations were among the first to notice Mars. To them, its red glow was not just a scientific curiosity, but something mysterious and even divine. The Babylonians associated it with their god of war, while the Romans later named it after their own god of battle, Mars. The Greeks called it Ares, also the god of war, and this association came from the planet's fiery colour, which resembled the colour of blood and symbolised strength, power, and conflict. Yet, beyond its mythological past, the real Mars turned out to be even more intriguing than the ancient stories ever imagined. Scientists, armed with telescopes, spacecraft, and rovers, have discovered that this red world is a cold desert filled with mountains taller than any on Earth, valleys deeper than the Grand Canyon, and traces of what might once have been rivers and seas. One of the most fascinating features of Mars is its two small moons, Phobos and Deimos. Unlike Earth's large and round moon, These Martian moons are irregular in shape, resembling lumpy potatoes rather than perfect spheres. They're tiny compared to most natural satellites in the solar system. Phobos, the larger one, is only about 22 kilometers across at its widest point, while Deimos is even smaller, measuring only about 12 kilometers across. These moons were discovered in the late 19th century by the American astronomer Asaph Hall, who named them after the Greek words for fear and terror, the mythological sons of Ares, the god of war. The names suit Mars perfectly, tying its mythology to its cosmic features. Phobos and Deimos orbit Mars at different distances and speeds. Phobos circles very close to the planet's surface, completing one orbit in just a little over 7 hours. Because of this, it rises in the west and sets in the east several times a day. Deimos, on the other hand, orbits farther away, taking about 30 hours to make a full circuit. Both moons are believed by many scientists to be captured asteroids, space rocks that once travelled freely through the solar system before being trapped by Mars's gravity. Phobos, the larger of the two, is slowly spiralling inward toward the planet and may one day crash into Mars or break apart, forming a ring around it. Deimos, however, is slowly drifting away, much like Earth's moon, though at a much slower pace. A day on Mars, often called a sol, lasts about 24.6 hours, just slightly longer than a day on Earth. This means that time on Mars passes at almost the same rhythm we're used to on our planet. For scientists working with rovers on Mars, this similarity makes it easier to plan missions and control the robotic explorers from Earth. However, a year on Mars is much longer than on Earth. It takes 687 Earth days for Mars to complete one orbit around the Sun. This is almost twice the length of an Earth year, which means that each Martian season lasts much longer than ours. Spring, summer, autumn and winter come and go slowly on this cold world, making its climate and weather patterns quite different from what we experience at home. The planet's distance from the Sun plays a major role in shaping its environment. Mars is the fourth planet from the Sun, located between Earth and Jupiter. Because it's farther away, it receives less sunlight and heat. This makes it a much colder world, where average surface temperatures often fall well below freezing. In many regions, frost and ice form on rocks and in craters, particularly near the poles, where frozen carbon dioxide and water ice cover the surface during the long winters. Despite its dry appearance, Mars still holds large quantities of ice beneath its dusty surface, hidden like treasure waiting to be uncovered. Perhaps the most dramatic and awe-inspiring feature on Mars is Olympus Mons, the tallest volcano not only on the planet but in the entire solar system. Rising to a height of about 22 kilometers, Olympus Mons is nearly 3 times taller than Mount Everest, Earth's highest mountain. Its base is so wide that it could cover the entire state of Arizona. The volcano's slopes are gentle, formed by countless layers of lava that poured out slowly over millions of years. Scientists believe Olympus Mons formed long ago when Mars still had volcanic activity fueled by heat from its interior. Since Mars lacks tectonic plate movement like Earth, the volcanic hotspots remained fixed, allowing massive mountains like Olympus Mons to grow to gigantic sizes without being moved away from their source of magma. The immense volcano sits on a vast plateau known as the Tharsis region, which is home to several other large volcanoes, though none as massive as Olympus Mons. The Tharsis region also shows signs of ancient lava flows, cracks, and fissures that hint at a time when Mars was geologically active. Although today the planet is mostly quiet, with no known active volcanoes, the scars of its fiery past remain visible, reminding us that Mars was once a world full of energy and movement. Not far from this volcanic region lies another of Mars' most striking landmarks, Valle Marineris. This enormous canyon system stretches for about 4,000 kilometers across the planet's equator, roughly the distance between New York and Los Angeles. It is up to 7 kilometers deep in some places and as wide as 200 kilometers. To imagine its scale, if Valles Marineris were on Earth, it would stretch from the Atlantic Ocean to the Pacific Ocean. The canyon is so vast that it can be seen clearly from orbiting spacecraft, appearing like a great scar carved across the Martian surface. The origin of Valles Marineris remains one of Mars' greatest mysteries. Scientists believe it may have formed when the planet's crust cracked, as the Tharsis region swelled with volcanic activity billions of years ago. Over time, erosion, landslides, and possible water flow may have widened and deepened the canyon. Its cliffs, slopes, and valleys tell a story of ancient geological forces that shaped Mars into the rugged world we see today. Within its walls are layers of rock that preserve records of the planet's history, each layer marking a different era, possibly stretching back billions of years. Mars's atmosphere is very thin, much thinner than Earth's, and is made mostly of carbon dioxide, which makes up about 95% of it. Nitrogen and argon make up most of the rest, with only trace amounts of oxygen and water vapour. Because the atmosphere is so thin, it cannot hold much heat, causing extreme temperature changes between day and night. During the day, sunlight can warm the surface slightly above freezing in some places, but at night, the temperature can drop drastically to well below -100 degrees Celsius. The thin air also means that liquid water cannot exist for long on the surface. It would quickly evaporate or freeze. This lack of a thick atmosphere also leaves Mars exposed to harmful radiation from the sun, which makes the surface a harsh place for life as we know it. Yet, despite its thin atmosphere, Mars is not a still or lifeless world. One of its most remarkable natural events is its dust storms. Mars is famous for having dust storms that can grow to an enormous scale, sometimes covering the entire planet for weeks or even months. These storms begin when sunlight heats the surface unevenly, creating winds that lift fine particles of dust into the air. As the winds grow stronger, more dust is picked up, feeding the storm and allowing it to spread across vast distances. Some of these storms can block out sunlight and make the sky appear hazy and red. For spacecraft and rovers operating on the surface, these storms pose significant challenges, as the dust can coat solar panels and reduce their ability to generate power. Despite these difficulties, such storms have also provided scientists with valuable insights into Mars' weather and climate systems. The presence of iron oxide not only colours the planet's surface, but also fills its atmosphere with fine dust that gives the sky a pinkish or orange hue. When astronauts eventually travel to Mars, they will likely see sunsets that glow in shades of blue, caused by how the dust particles scatter sunlight. This strange reversal, blue sunsets and reddish days, adds to the planet's alien beauty. For decades, scientists have searched for evidence that Mars might once have supported life. The discovery of ancient river valleys, dry lake beds, and mineral deposits that form only in water has led many to believe that the planet once had flowing liquid water on its surface. Billions of years ago, Mars may have had a thicker atmosphere that allowed water to exist in rivers, lakes, and even shallow seas. Crater patterns, channels, and delta formations visible from orbit show clear signs of erosion that look similar to what flowing water would create on Earth. Some areas also contain clay and sulfate minerals, which typically form in the presence of water. These discoveries suggest that Mars may have once been a warmer and wetter world, very different from the frozen desert we see today. In recent years, spacecraft orbiting Mars have detected signs of frozen water below the surface and even seasonal streaks that may indicate salty water flowing occasionally down slopes. Though no liquid water has yet been directly observed, these clues are tantalizing hints that Mars might still hold small pockets of moisture or even underground aquifers. Scientists are eager to find out whether these hidden reserves could support life, either past or present. Even if Mars no longer has life today, finding evidence that it once did would be one of the greatest discoveries in human history, proving that life is not unique to Earth. Mars has long captured the imagination of both scientists and dreamers. The first spacecraft to visit Mars, such as NASA's Mariner missions in the 1960s and 1970s, provided the first close-up images of its rocky, cratered surface. Later missions, like the Viking landers in the 1970s, conducted experiments searching for signs of life but found none. Still, these missions laid the foundation for future exploration by showing that Mars had a complex environment worth studying further. In the modern era, robotic explorers have continued to expand our knowledge. The rovers Curiosity and Perseverance are among the most advanced machines ever sent to another planet. Curiosity, which landed in the year 2012, has spent years exploring Gale Crater, studying its rocks, soil, and atmosphere. It has discovered chemical evidence that the crater once contained an ancient lake, suggesting that Mars had conditions suitable for life in the distant past. Perseverance, which arrived in the year 2021, landed in Jezero Crater, a place that once held a vast lake and a river delta. Equipped with cutting-edge tools, Perseverance is searching for signs of ancient microbial life and collecting samples of rock and soil that future missions may bring back to Earth. Alongside these rovers, other spacecraft orbit Mars to study it from above. NASA's Mars Reconnaissance Orbiter, launched in the year 2005, has captured breathtaking high-resolution images of the planet's surface, showing landslides, sand dunes, and seasonal frost. The European Space Agency's Mars Express and India's Mars Orbiter mission have also contributed valuable data, mapping the planet's terrain and studying its atmosphere. These missions together paint a vivid picture of a world that, though desolate today, once may have been alive with rivers and lakes. Mars continues to challenge and inspire humanity. It has become the prime target for future exploration, and space agencies around the world are working towards sending humans there. NASA, SpaceX, and other organizations are developing technology that could make such a journey possible within the 21st century. The dream of setting foot on the Red Planet is no longer science fiction. It is becoming a realistic goal. Scientists envision habitats that could protect astronauts from radiation, greenhouses that could grow food, and machines that could extract water and oxygen from the Martian environment. Such a mission would not only be a major step for science, but also a defining moment for humanity's expansion beyond Earth. Mars also offers lessons about our own planet. By studying how its atmosphere was lost and how its climate changed over billions of years, scientists gain insights into the processes that shape planetary environments. Understanding why Mars became a cold desert, while Earth remained warm and full of life, may help us protect our own world from similar fates. The thin atmosphere and lack of magnetic field on Mars show how fragile a planet's environment can be, reminding us of the delicate balance that allows life to exist on Earth. As each new rover and orbiter sends back images, Mars becomes less of a mystery and more of a familiar neighbour. The photographs show sweeping plains covered in reddish dust, towering cliffs, ancient riverbeds, and strange rock formations sculpted by wind and time. Sometimes, the pictures capture dust devils twisting across the landscape, or frost forming on dark dunes at dawn. These scenes remind us that Mars, though lifeless on the surface, is a dynamic and ever-changing world. Its beauty lies in its silence, its vastness, and its history written across its dusty plains. Even the smallest details of Mars fascinate scientists. Its thin air allows meteoroids to strike the surface more easily, creating countless craters. Some of these craters are ancient, dating back billions of years, while others are fresh, formed in recent decades. The planet's polar regions are capped with layers of ice and dust that grow and shrink with the seasons. During winter, carbon dioxide freezes out of the air, forming bright white caps, while in summer, the frozen carbon dioxide sublimates, turning directly back into gas. This process creates seasonal winds and changes in pressure that affect the entire atmosphere. Mars's sky, though often hazy, has its own subtle beauty. During the day, the sky glows a dusty pink, while at sunset it turns a deep blue near the sun and reddish farther away. This happens because the fine dust particles scatter sunlight differently than on Earth. The thin atmosphere also allows sunlight to pass through with little filtering, giving the surface a sharp, crisp brightness. In the quiet stillness of Mars, time seems to move slowly. Rocks lie undisturbed for millions of years, and winds sculpt the dunes in patterns that shift only gradually. Yet beneath this calm surface, Mars holds stories of fire and ice, of rivers that once flowed, and of a planet that may have once looked much like Earth. It stands as both a reminder of what once was and a promise of what might be. As rovers continue their tireless journeys across its surface, and as scientists analyze every grain of Martian dust, humanity's connection to Mars grows stronger. It is not just another planet in the sky. It is a mirror reflecting our curiosity, our history, and our future. From its rusty plains to its distant moons, from its towering volcanoes to its ancient valleys, Mars remains one of the most captivating worlds in the solar system. Its mysteries challenge the limits of human knowledge, and its beauty continues to draw us closer. Every discovery adds another chapter to the story of a world that, despite its desolation, feels almost like a second home waiting to be rediscovered. The Red Planet, with its dust storms, frozen deserts, and silent mountains, continues to whisper across the vastness of space, inviting us to listen, explore, and understand. Jupiter stands as the true giant of the solar system, a world so massive and magnificent that it could easily fit all the other planets inside it with room to spare. It is a planet of mystery, beauty, and raw power, swirling with storms larger than our entire Earth and surrounded by a family of moons that could each be worlds of their own. Jupiter's immense size and presence have always captured the human imagination, glowing brightly in the night sky like a guardian of the outer solar system. From ancient times, people looked up at this shining object, not knowing what it was made of or how enormous it truly was. Yet today, through centuries of exploration and discovery, Jupiter has revealed itself to be one of the most extraordinary and fascinating worlds ever known. Jupiter is the largest planet in the solar system, a gas giant so vast that more than 1,000 Earths could fit inside its volume. It is made mostly of gases, and it does not have a solid surface like our planet. Instead, it is a swirling globe of hydrogen and helium, the same elements that make up the Sun. These gases form thick layers that blend and move endlessly, creating colourful bands, spots, and clouds that stretch around the planet. The planet's size and gravity dominate the solar system, affecting not just its moons, but also asteroids, comets, and even the orbits of other planets. Jupiter is often described as a failed star because if it had been only about 80 times more massive, the pressure and heat inside it might have been enough to start nuclear fusion, the process that makes stars shine. But instead, Jupiter remains a planet, the largest and most powerful one we have ever seen. The atmosphere of Jupiter is one of the most striking features of this gas giant. It is a world of colour and movement, with thick clouds swirling in patterns of white, brown, orange, red and yellow. The upper layers are made mostly of ammonia crystals and other chemical compounds that reflect sunlight in strange and beautiful ways. These clouds form dark belts and lighter zones that circle the planet parallel to its equator. The belts are areas of descending gas and storms, while the zones are regions of rising air and brighter clouds. The boundaries between them are often filled with enormous storms and chaotic swirls that move around the planet at incredible speeds. Among these storms is one that has become legendary, the Great Red Spot. This storm is larger than the entire planet Earth, a colossal oval-shaped whirlwind that has raged for centuries. Scientists have observed it for over 300 years, and yet it continues to spin and shift. The Great Red Spot is a high-pressure system with winds that can reach hundreds of kilometers per hour. Its colour can change from deep brick red to pale orange, and sometimes it even fades or shrinks slightly before growing again. The exact cause of its colour is still uncertain, but it may be due to complex chemical reactions in Jupiter's atmosphere, caused by sunlight interacting with different gases. This storm is so massive that if you could somehow hover above Jupiter and look down, it would appear like a gigantic, swirling eye watching over the planet. Beneath the visible clouds, Jupiter's atmosphere becomes denser and hotter. The deeper you go, the more the gases are compressed by the planet's enormous gravity. Eventually, hydrogen, which behaves like a gas near the surface, begins to act more like a liquid metal deep inside the planet. This metallic hydrogen is believed to be responsible for one of Jupiter's most powerful characteristics, its magnetic field. Jupiter's magnetic field is incredibly strong, far more powerful than Earth's. It extends millions of kilometers into space, creating an enormous region known as the magnetosphere. This invisible shield traps charged particles and deflects harmful solar radiation. The field also generates intense auroras near Jupiter's poles, much like the northern and southern lights on Earth, but far brighter and more energetic. The magnetic field of Jupiter affects not just the planet but also its many moons. The magnetic environment around Jupiter is filled with charged particles moving at high speeds, creating a radiation field so strong that it could be deadly to humans without heavy protection. This radiation is part of what makes Jupiter such a difficult place for spacecraft to explore closely. Yet, even with these challenges, human-made probes like Pioneer, Voyager, Galileo, and Juno have sent back priceless information about the planet and its surroundings, helping scientists understand its complex nature. Jupiter's enormous size and powerful gravity make it a kind of protector for the inner planets. It acts as a cosmic shield, drawing in or deflecting asteroids and comets that might otherwise crash into Earth or other planets. Its gravity can capture passing objects, pulling them into orbit or sending them hurtling out of the solar system entirely. Many scientists believe that without Jupiter, Earth might have faced far more collisions in its early history, which could have made life's development much more difficult. In this way, Jupiter might be one of the hidden guardians of life in the solar system. The planet's rapid rotation adds to its dynamic character. Jupiter completes a full rotation in just under 10 hours, the fastest rotation of any planet in the solar system. This quick spinning causes the planet to bulge slightly at the equator and flatten at the poles, giving it an oblate shape. The rapid rotation also drives powerful jet streams and contributes to the creation of its many bands and storms. Because of this, Jupiter is always in motion, a planet of endless winds and turbulence. From a distance, it might look peaceful and beautiful, but beneath that beauty lies a world of immense power and constant change. Surrounding Jupiter is an impressive collection of moons. At least 95 known moons orbit this giant planet, and scientists continue to discover more as telescopes become more advanced. Each of these moons is unique, and together they form a miniature solar system around Jupiter. Among them, 4 stand out as the largest and most famous: Io, Europa, Ganymede, and Callisto. These are known as the Galilean moons, named after Galileo Galilei, who first observed them in the year 1610 using one of the earliest telescopes. His discovery was a major moment in human history because it showed that not everything revolved around Earth, challenging old beliefs and helping shape our understanding of the universe. Each of these 4 moons has its own special qualities. Ganymede, for example, is the largest moon in the entire solar system. It is even bigger than the planet Mercury. Ganymede has its own magnetic field, which is unusual for a moon, and its surface is a mix of ice and rock, covered with craters and bright streaks formed by past geological activity. Scientists believe that beneath its icy crust there may be layers of salty water, possibly forming an underground ocean that could be hundreds of kilometers deep. If that is true, Ganymede might hold clues about how life could exist in other parts of the solar system. Europa, another of the Galilean moons, has long fascinated scientists because of its smooth, bright surface and the possibility that it hides a vast ocean beneath its icy shell. This hidden ocean might contain more water than all of Earth's oceans combined. The surface of Europa is covered with cracks and lines, as if the ice is slowly shifting and breaking apart. Scientists think that the tidal forces caused by Jupiter's strong gravity heat the moon's interior, keeping the water beneath the ice in liquid form. If life ever developed elsewhere in our solar system, Europa might be one of the best places to find it. The thought that a world orbiting Jupiter could have an ocean filled with unknown forms of life is one of the most exciting ideas in modern astronomy. Io, the innermost of the Galilean moons, is a world of fire and chaos. It has hundreds of active volcanoes that constantly erupt, spewing molten sulfur and gases into space. These eruptions are driven by the intense tidal forces caused by Jupiter's gravity pulling and squeezing the moon as it orbits. The constant flexing of Io's interior generates enormous heat, making it the most volcanically active body in the entire solar system. Its surface is colourful and constantly changing, painted in shades of yellow, orange, red and black from sulfur compounds. Some of its volcanic plumes shoot hundreds of kilometres high, creating a dramatic and ever-changing landscape. Callisto, the outermost of the 4 large moons, presents a different story. It is an ancient, heavily cratered world that has changed little over billions of years. Its surface looks like a frozen record of the solar system's early history. Beneath its icy crust, scientists believe there might also be a hidden ocean, though it is likely buried deep below the surface. Callisto's lack of geological activity makes it one of the most stable and quiet worlds orbiting Jupiter, a stark contrast to the violent nature of Io or the mysterious depths of Europa and Ganymede. Beyond these 4 large moons, Jupiter's other moons vary greatly in size and composition. Some are only a few kilometers wide, more like asteroids captured by the planet's gravity. These smaller moons often have irregular shapes and strange orbits, and they may have come from collisions or gravitational captures over time. Together, they form a complex system that continues to intrigue astronomers. Jupiter also has a faint ring system, which is much less noticeable than Saturn's majestic rings. These rings are made of tiny particles of dust and rock created when meteoroids struck some of Jupiter's moons. Although they are hard to see from Earth, spacecraft have been able to photograph them, revealing that even this massive planet carries a delicate and beautiful ring structure. The storms and winds on Jupiter are unlike anything found on Earth. Winds can blow at hundreds of kilometers per hour, circling the planet in opposite directions in its various bands. Some storms last for years or even centuries. Lightning flashes in the planet's atmosphere are much more powerful than those on Earth, and thunderclouds on Jupiter can rise many kilometers high. The energy and motion in its atmosphere create one of the most dynamic environments in the solar system. The colors seen in Jupiter's clouds are caused by the interaction of sunlight with different chemicals in the atmosphere, including ammonia, water vapor, and possibly sulfur compounds. These chemicals form bright and dark patterns that are always shifting. Sometimes the planet's appearance changes noticeably in just a few days as storms form and fade. Despite centuries of study, scientists are still trying to understand the full complexity of Jupiter's weather systems. Deep inside Jupiter, the pressure becomes unimaginably high. The gases are squeezed so tightly that they turn into liquids, and eventually hydrogen becomes metallic under the enormous pressure. Scientists believe that Jupiter has a dense core made of rock and metal, surrounded by layers of metallic hydrogen and ordinary hydrogen gas. Temperatures in the core may reach tens of thousands of degrees Celsius, and the pressure could be millions of times greater than Earth's atmosphere. This extreme environment creates powerful magnetic and electric fields and contributes to Jupiter's internal heat. Jupiter actually gives off more heat than it receives from the Sun. This means that the planet still holds on to some of the heat left over from its formation more than 4.5 billion years ago. Some of this energy also comes from the slow compression of the planet's interior under its own immense gravity. This internal heat helps power the enormous storms and weather patterns that make Jupiter so active and alive. From Earth, Jupiter is one of the brightest objects in the night sky, outshone only by the Moon and Venus. When viewed through a telescope, its bands, storms and moons become visible, and it is easy to understand why early astronomers were so captivated by it. Watching its moons move night after night was one of the first direct pieces of evidence that not everything revolves around Earth, a discovery that changed human understanding forever. Jupiter's influence extends far beyond its immediate surroundings. Its powerful gravity has shaped the history of the solar system, influencing the orbits of other planets and helping to clear out debris that might otherwise have collided with the inner worlds. It is even possible that Jupiter's movement in the early solar system affected how the planets formed, pulling some material inward and pushing other material outward, helping to create the layout of planets we see today. The exploration of Jupiter by spacecraft has revealed more details about this extraordinary world than anyone could have imagined centuries ago. The Pioneer and Voyager missions in the 1970s gave the first close-up views, showing the complex cloud patterns and the 4 large moons in remarkable detail. The Galileo spacecraft, which arrived in the 1990s, orbited Jupiter for years, studying its atmosphere, magnetic field and moons. It sent a probe into the planet's atmosphere, which transmitted data until it was destroyed by the extreme pressure. More recently, NASA's Juno spacecraft, which began orbiting Jupiter in the year 2016, has provided the most detailed measurements ever made of the planet's structure, gravity, and magnetic field. The images from Juno have shown Jupiter's swirling storms and poles in breathtaking detail, revealing a world of beauty and power that continues to surprise even the most experienced scientists. Saturn stands as one of the most breathtaking and mysterious worlds in the solar system. It shines in the dark ocean of space like a majestic crown made of ice and light, its wide and shining rings circling it in perfect harmony. It is the 6th planet from the Sun, and although it is far away from our world, it has captured human imagination for centuries. Astronomers have looked at it through telescopes and spacecraft, and poets and dreamers have written about its beauty. Saturn is not just another planet, it is one of the grandest wonders of the universe, a world that seems almost too beautiful to be real. One of the most fascinating things about Saturn is its enormous system of rings, which make it instantly recognizable among all the planets. These rings are not solid, like the edge of a disk, but are made up of countless tiny pieces of ice, rock, and dust that orbit Saturn together. Some of these pieces are as small as grains of sand, while others are as large as mountains. They sparkle like diamonds when sunlight touches them, forming bright, glowing bands that can stretch hundreds of thousands of kilometers into space. Each ring moves in its own delicate orbit, and together they form a magnificent structure that is both fragile and eternal. Scientists believe these rings may be the remains of ancient moons or comets that were shattered long ago by Saturn's immense gravity, leaving behind a ring of debris that now encircles the planet like a shining halo. The rings themselves are divided into several main parts, named alphabetically in the order they were discovered: the D, C, B, A, F, G, and E rings. The B ring is the brightest and most massive, while the F ring is thin and full of strange twists and clumps caused by tiny moons called shepherd moons that help shape and guide it. The E ring, on the other hand, is faint and wide, and it is constantly replenished by geysers of water ice, erupting from Saturn's moon Enceladus. The complexity of the ring system is something that scientists are still trying to fully understand. They behave almost like a living structure, constantly changing, shifting, and shimmering under the influence of gravity, sunlight, and magnetic forces. Saturn itself is a planet so light and airy that if there were a cosmic ocean large enough, it would actually float. This may sound unbelievable, but it is true. Saturn's density is less than that of water, which means it is made mostly of light gases like hydrogen and helium, the same elements that make up the Sun. Deep inside, Saturn probably has a small rocky core surrounded by layers of metallic hydrogen and liquid helium which swirl together under enormous pressure. The outer layers are made of clouds that stretch across the planet in colourful bands of yellow, gold, and pale brown. These bands are formed by powerful winds that race around the planet at incredible speeds, sometimes reaching more than 1,000 kilometers per hour. Even though Saturn is enormous, more than 9 times wider than Earth, it is mostly empty inside, made up of gases rather than solid matter. This is why it would float on water if such a thing were possible. The planet's beauty hides a chaotic and violent world beneath its clouds. Storms sweep across its surface, and lightning flashes deep inside its atmosphere. The winds never stop, and massive tempests form and disappear again in a matter of days or weeks. One of the most striking features of Saturn's weather is the strange and mysterious storm that sits right at its north pole. Unlike any storm seen anywhere else in the solar system, this one has a shape like a perfect hexagon. Each side of the hexagon is thousands of kilometers long, and the storm itself is so large that several Earths could fit inside it. The hexagon seems to be formed by fast-moving jet streams that circle around the pole, creating a stable pattern that has lasted for decades, perhaps even centuries. At the center of the hexagon lies a huge hurricane-like eye, swirling endlessly in the cold darkness of Saturn's atmosphere. Scientists have tried to recreate this strange shape in laboratory experiments using fluids, and they found that certain combinations of rotation and pressure can indeed produce stable polygonal patterns. But Saturn's natural hexagon remains one of the most fascinating mysteries in planetary science. Saturn rotates very quickly for a planet of its size. It takes only about 10 7/10 hours to complete one full rotation, which means that a day on Saturn is less than half the length of a day on Earth. Because of this rapid spinning, the planet is not perfectly round but flattened at the poles and bulging at the equator. This fast rotation also helps create the strong winds and banded cloud patterns that give Saturn its striped appearance. The outer atmosphere is constantly in motion, with gases rising and falling in great waves and storms appearing like white spots before fading away. Saturn is not alone in the cold reaches of space. It is accompanied by a vast family of moons, more than 146 confirmed so far, each with its own unique story and mystery. These moons range in size from small irregular rocks to large worlds that could almost be planets in their own right. The most famous of them all is Titan, Saturn's largest moon, which is even bigger than the planet Mercury. Titan is an extraordinary place, shrouded in a thick orange-coloured atmosphere made mostly of nitrogen, with traces of methane and other gases. This makes Titan the only moon in the solar system with a dense atmosphere, and it is one of the few places besides Earth where stable liquid can exist on the surface. But instead of water, Titan's lakes and rivers are made of liquid methane and ethane. Walking on Titan would be like stepping into a frozen world of mist and twilight. The sun would appear as a dim glow in the sky, and the landscape would be dotted with lakes, dunes, and icy hills. The air would be thick and cold, and strange rain made of methane would fall slowly to the ground. Scientists believe that beneath Titan's icy crust, there may be an ocean of liquid water mixed with ammonia, kept warm by the heat from the moon's interior. This hidden ocean makes Titan one of the most promising places to search for life beyond Earth. Even though any life there would be very different from life as we know it, the ingredients for it, liquid, energy, and complex molecules, are all present. Another moon that has captured the imagination of scientists is Enceladus, a small and bright world covered in ice. Despite its small size, Enceladus is one of the most active bodies in the solar system. From cracks near its south pole, giant plumes of water vapor, ice particles and organic compounds burst into space like enormous geysers. These plumes feed Saturn's E-ring, creating a constant flow of material that orbits the planet. What makes Enceladus truly remarkable is that these geysers seem to come from an underground ocean beneath the Moon's icy shell. This ocean, warmed by heat from the Moon's rocky core, could be a potential home for simple forms of life. When the Cassini spacecraft flew through the plumes, it detected organic molecules, water, and even hints of chemical energy. Just the kind of conditions that microbes could use to survive. The Cassini spacecraft was one of the most successful missions in the history of space exploration. Launched in the year 2004, Cassini spent 13 years exploring Saturn and its moons before its mission ended in 2017. During that time, it sent back hundreds of thousands of images and a treasure of scientific data that completely changed our understanding of the planet. Cassini watched storms forming and fading, measured the magnetic field, mapped the rings, and flew close to several moons, including Titan and Enceladus. One of its most dramatic discoveries was the confirmation that Enceladus has a global ocean beneath its icy surface. Another was the detection of rain made of methane on Titan. Cassini also revealed that Saturn's rings are far more complex and dynamic than anyone had imagined, with particles constantly colliding, clumping together, and breaking apart again. When its mission came to an end, Cassini performed one final daring maneuver known as the Grand Finale. The spacecraft dove between Saturn and its innermost ring, passing through this narrow gap 22 times before plunging into the planet's atmosphere, where it burned up like a shooting star. This final act ensured that the spacecraft would not accidentally crash into one of Saturn's moons, possibly contaminating it with microbes from Earth. Cassini's sacrifice marked the end of an era, but its discoveries continue to inspire scientists and dreamers to this day. The idea that Saturn's rings might be the remains of a shattered moon adds an element of ancient tragedy to the planet's beauty. Long ago, perhaps billions of years in the past, one of Saturn's moons may have ventured too close to the planet, crossing the point where tidal forces, gravitational pull differences between the near and far sides of the moon, became too strong. The moon would have been torn apart, its pieces scattering into orbit to form the magnificent rings we see today. This idea fits with what we know about the physics of Saturn's gravitational field and the way the rings behave. If this theory is true, then every glittering shard of ice and rock circling Saturn could be a fragment of a once whole world, broken forever yet still dancing in perfect harmony around their parent planet. Saturn's magnetic field is another remarkable feature. It is strong, though not as powerful as Jupiter's, and it helps shape the environment around the planet. The magnetic field traps charged particles from the solar wind, forming radiation belts and glowing auroras near the poles. These auroras shine in the ultraviolet and infrared parts of the spectrum, and when observed by space telescopes, they appear as ghostly blue and green lights swirling above the planet's cloud tops. They are a visible sign of the invisible magnetic forces that surround Saturn, linking it to the vast electrical currents of the solar system. Even though Saturn lies more than 1 billion kilometers away from the Sun, it still receives enough sunlight to make its clouds glow softly in shades of cream and gold. From Earth, Saturn appears as a pale yellow star in the night sky, but when viewed through a telescope, it transforms into one of the most astonishing sights the human eye can behold, a golden world encircled by rings of light. It is no surprise that many ancient cultures associated Saturn with gods of time, harvest, and wisdom. In Roman mythology, Saturn was the god of agriculture and renewal, and his reign was remembered as a golden age. The planet that bears his name truly lives up to that legacy, with its golden hues and timeless beauty. Saturn's size is so immense that about 760 Earths could fit inside it, yet it spins so fast that it completes a full rotation in less than 11 hours. Its vastness and speed together create a delicate balance between order and chaos, between beauty and destruction. The atmosphere is filled with countless bands and belts, each one marking a region of rising or sinking gas. Enormous storms occasionally appear, some lasting for years. One such storm, known as the Great White Spot, appears roughly once every 30 Earth years, one Saturnian year, and can be so large that it wraps all the way around the planet. The more scientists learn about Saturn, the more mysterious it seems. Its interior remains largely unexplored, hidden beneath layers of dense clouds. Deep within, there might be a metallic core where hydrogen behaves like liquid metal, conducting electricity and creating the planet's magnetic field. Above this core lies a vast sea of liquid hydrogen and helium, swirling endlessly under crushing pressure and intense heat. The outer layers are cooler, forming clouds made of ammonia, water, and other chemicals that create the planet's soft, banded appearance. The combination of hydrogen and helium also means that Saturn shares much in common with the Sun. In fact, it can be thought of as a kind of miniature star that never ignited. Its composition shows how the solar system formed, from a cloud of gas and dust that gave birth to both the Sun and the planets. By studying Saturn, scientists gain a deeper understanding of how worlds are born, evolve, and change over billions of years. Although Saturn's rings seem eternal, they may not last forever. Studies of the Cassini data suggest that the rings are slowly losing material, as particles are pulled toward the planet by gravity, or pushed away by sunlight and magnetic forces. Some scientists believe the rings could disappear in as little as 100 million years, a blink of an eye compared to the planet's age. That means we live in a special time in the history of the solar system, when Saturn still wears its crown of ice. Beyond Titan and Enceladus, Saturn's other moons also have stories to tell. Mimas, a small moon, looks almost exactly like the Death Star from the famous space movies because of a huge crater named Herschel that covers nearly 1/3 of its surface. Tethys and Dione are larger and brighter, covered with ice and crossed by mysterious lines and canyons. Rhea is another icy moon that may also have thin rings of its own, something never before seen around a moon. Iapetus, one of the strangest of all, has one side as dark as coal and the other as bright as snow, making it look like a yin-yang symbol floating in space. Each of these moons adds a unique piece to the grand story of Saturn, making the planet a miniature solar system in itself. Saturn's place in the solar system is not only physical but also symbolic. It represents balance, structure, and the beauty of natural order. Its rings remind us that destruction can also create beauty, that the end of one world can become the adornment of another. Its moons remind us of the diversity of creation, where every world, no matter how small, can hold surprises and mysteries waiting to be discovered. From ancient times, Saturn has been a symbol of mystery and wonder. Before telescopes, it appeared as a wandering star, slow and steady in its motion. When Galileo Galilei first observed it through his simple telescope in the year 1610, he was puzzled by what he saw. The rings were not clearly visible to him, and he thought Saturn might have ears or be a triple planet. It was only decades later that astronomers realized that these strange shapes were actually a vast ring system encircling the planet. Since then, every improvement in technology, from ground telescopes to space probes, has revealed more and more details about this extraordinary world. Even now, in the age of powerful space telescopes and interplanetary missions, Saturn continues to surprise us. Each new observation uncovers new mysteries, tiny moons hiding in the rings, new patterns in the storms, or unexplained features in the planet's magnetic field. It is a reminder that the universe is far greater and more complex than we can easily imagine. Uranus is one of the most fascinating planets in our solar system, standing far out beyond the orbit of Saturn and before Neptune. It is known as an ice giant, which means that a large part of its mass is made up of elements and compounds that are heavier than hydrogen and helium, such as water, ammonia, and methane. Unlike the gas giants Jupiter and Saturn, which are mostly made of gas, Uranus contains a huge amount of icy material deep within it, making it a colder, denser, and more mysterious world. From a distance, Uranus shines with a soft bluish-green colour that gives it a calm, almost peaceful look. This distinctive colour comes from methane gas in its upper atmosphere, which absorbs the red part of sunlight and reflects the blue and green light back into space. But beneath that serene appearance lies a world of great extremes, a planet that spins on its side, experiences strange seasons that last for decades, and hides secrets deep within its icy layers. Uranus is tilted in a way unlike any other planet in the solar system. Its axis of rotation is tilted at an astonishing 98 degrees, which means that it does not spin upright like Earth or Mars. Instead, it rolls around the Sun on its side as though it had been knocked over long ago by some massive cosmic collision. Because of this tilt, the planet's poles lie almost where its equator should be, creating bizarre and dramatic seasonal effects. During part of its long year, one pole faces the Sun continuously, while the other remains in total darkness, and then the situation reverses as Uranus moves along its orbit. For decades at a time, one half of the planet basks in sunlight while the other half is plunged into a freezing, endless night. This unique tilt makes Uranus one of the strangest rotating worlds ever discovered, a planet that truly defies expectations. A single day on Uranus lasts about 17 hours, meaning that the planet spins relatively quickly despite its enormous size. Even though it is about 4 times larger than Earth in diameter, Uranus completes a full rotation faster than our planet does. This rapid spin contributes to the planet's shape, making it slightly flattened at the poles and bulging around the equator. The fast rotation also drives strong winds in the atmosphere, with speeds reaching hundreds of kilometers per hour. These winds swirl through clouds made of methane ice and other exotic chemicals, forming faint streaks and bands that are difficult to see from a distance. For many years, astronomers thought Uranus had a bland, featureless atmosphere, but with more advanced telescopes, faint cloud patterns and storms have been detected, hinting at the restless nature of its skies. A year on Uranus, however, is unimaginably long. The planet takes about 84 Earth years to complete a single orbit around the Sun. Because of this, every season on Uranus lasts for more than 20 Earth years. Imagine a single summer or winter lasting 2 decades, with the Sun hanging low in the sky, or not rising at all for years at a time. The extreme tilt and long orbit combine to create some of the most dramatic and alien seasonal changes in the entire solar system. During its long journey around the Sun, Uranus experiences times when one pole faces the Sun directly, receiving constant daylight, while the other pole is locked in endless darkness. As the planet continues to move, the situation slowly shifts until the opposite happens. These prolonged seasons deeply affect the atmosphere, possibly causing changes in temperature, cloud formation, and wind patterns over time. Uranus is also home to 27 known moons, each with its own story and character. Many of these moons are named after characters from the works of William Shakespeare and Alexander Pope, such as Titania, Oberon, Ariel, Umbriel, and Miranda. Among them, Miranda stands out for its strange and dramatic surface. It has enormous cliffs, deep valleys, and patchwork-like regions that make it look as though it has been shattered and reassembled. This unusual appearance suggests that Miranda may have experienced violent geological events in the past, perhaps caused by tidal forces from Uranus. Titania and Oberon, the 2 largest moons, are much bigger and darker, with ancient surfaces covered in craters and canyons. Ariel and Umbriel are smaller but still intriguing, each bearing marks of a complex history shaped by ice, rock, and time. These moons form a fascinating family orbiting the tilted planet, each one a frozen world of its own, silently circling through the cold outer reaches of the solar system. Surrounding Uranus is a delicate system of rings, much fainter and darker than the bright and wide rings of Saturn. The rings of Uranus were discovered in the year 1977, when astronomers noticed that starlight dimmed briefly as the planet passed in front of a distant star. These dimmings revealed the presence of narrow dark bands encircling Uranus. The rings are made up mostly of small pieces of rock and ice coated with dark material, possibly organic compounds that make them appear almost black. They are so faint that they are invisible to most telescopes on Earth and can only be seen clearly with special instruments or from spacecraft. There are 13 known rings in total, though some may be incomplete or filled with tiny particles spread out over large distances. The inner rings are narrow and sharply defined, while the outer ones are more diffuse. These mysterious shadowy rings add another layer of beauty to Uranus, giving it a ghostly and almost secretive appearance as it glides through the dark of space. The atmosphere of Uranus is a mixture of hydrogen, helium, and methane. Hydrogen and helium make up most of it, but it is the small amount of methane that gives Uranus its lovely blue colour. Methane absorbs red light and lets blue and green light pass through, making the planet shine with a cool and calm hue. Beneath the visible clouds, scientists believe there are layers of water, ammonia, and methane ice, forming a deep icy mantle around a rocky core. The pressures and temperatures inside Uranus are so extreme that ordinary materials behave in unusual ways. For example, Under such immense conditions, water and ammonia may form a thick, slushy mixture, and methane might break apart to release carbon, which could form diamonds that fall like rain deep within the planet. The thought of diamond rain sparkling through an icy atmosphere is one of the most beautiful and mysterious ideas in planetary science, showing how alien and magical Uranus truly is. Although Uranus is classified as an ice giant, it does not have the same strong internal heat as other giant planets like Jupiter and Neptune. In fact, Uranus gives off very little heat compared to the amount it receives from the Sun, making it one of the coldest planets in the solar system. Temperatures in its upper atmosphere can drop to around -224 degrees Celsius, colder than anywhere else in the known planetary system. Scientists are still puzzled by this lack of internal heat. One theory suggests that the same massive collision that tipped Uranus on its side may also have disrupted its core, preventing heat from escaping normally. Another idea is that some kind of barrier layer inside the planet traps the heat, stopping it from rising to the surface. Whatever the reason, the result is a planet that seems quiet and frozen, radiating far less warmth than expected for a world of its size and composition. Only one spacecraft has ever visited Uranus, NASA's Voyager 2, which flew past the planet in January of 1986. Voyager 2 provided humanity with its first and only close-up view of Uranus, revealing its pale blue disk, faint rings, and family of moons. During its brief encounter, the spacecraft collected a vast amount of information that transformed our understanding of this distant world. It measured the composition of the atmosphere, mapped the magnetic field, and photographed the moons in detail for the first time. Among the surprises discovered by Voyager 2 was the fact that Uranus's magnetic field is tilted at a strange angle, not aligned with its rotation axis like most planets. Instead, the magnetic field is off-center and leans about 59 degrees away from the axis, creating complex and uneven magnetic effects. This unusual magnetism adds yet another mystery to a planet already filled with strange characteristics. Voyager 2's historic flyby lasted only a few hours, yet it remains one of the most valuable encounters in space exploration history, giving us glimpses of a world we have never seen again up close. The seasons of Uranus are among the most extreme and astonishing of any planet in the solar system. Because of its 98-degree tilt and its long orbital period of 84 Earth years, each pole spends about 42 years in continuous sunlight, followed by 42 years of darkness. During the long summer, the sun shines constantly on one hemisphere, heating it slowly, while the other hemisphere remains in the freezing shadow of night. Then, as the planet moves to the opposite side of its orbit, the seasons reverse, and the dark side becomes the one bathed in sunlight. These long-lasting seasons affect the atmosphere in ways that are still not fully understood. Scientists believe that the temperature differences between the lit and dark hemispheres may drive deep circulation patterns, causing winds and storms to shift over time. Some telescopic observations suggest that cloud activity increases during certain parts of Uranus's orbit, possibly connected to the gradual change in sunlight. Because of the planet's distance from the Sun, these changes occur slowly, making them difficult to study from Earth. Even so, every observation brings new clues about how such an unusual world responds to the rhythms of light and darkness. Uranus's magnetic field is as strange as its tilt. Most planets, including Earth, have magnetic fields that are roughly aligned with their rotation axes and centered near their cores. But Uranus's magnetic field is tilted by nearly 60 degrees and is shifted far away from the planet's center. This causes the magnetic poles to wander across the surface in unexpected ways, and creates an uneven magnetosphere that traps charged particles in complex patterns. The result is a magnetic environment that changes dramatically as Uranus rotates, unlike the steady fields found on other planets. The cause of this misaligned magnetism may lie deep within Uranus's interior, where the electrical currents that generate the field flow through layers of water, ammonia, and methane under extreme pressure. Understanding this strange magnetic field helps scientists learn not only about Uranus, but also about the fundamental processes that shape planetary magnetism throughout the cosmos. Although Uranus looks calm from a distance, it is a planet full of dynamic activity. Its atmosphere is layered with thin clouds of methane ice, and beneath those clouds are deeper regions where ammonia and water might form swirling currents. Winds rush across the planet at speeds up to 900 kilometers per hour, moving clouds and hazes across the upper atmosphere. These winds are driven by complex forces, the rotation of the planet, differences in temperature, and perhaps even internal heat, though Uranus has less of it than other giants. From time to time, astronomers have observed bright storms flashing across the planet, sometimes lasting for days. These storms may be driven by small bursts of heat rising from below, or by changes in sunlight as Uranus moves through its long seasonal cycle. Because the planet is so far away, these events are difficult to monitor, but modern telescopes and infrared instruments have allowed scientists to capture glimpses of Uranus's hidden storms. The discovery of Uranus itself was a major milestone in the history of astronomy. It was the first planet to be found with a telescope, rather than by the naked eye. In the year 1781, the astronomer William Herschel spotted a faint bluish object while observing the night sky through his telescope in England. At first, he thought it might be a distant star or comet, but after careful study, he realized that it was a new planet orbiting the Sun beyond Saturn. This discovery expanded the known boundaries of the solar system for the first time in human history, doubling the size of the known planetary family. The finding of Uranus inspired generations of astronomers to search even further, eventually leading to the discoveries of Neptune and Pluto. Herschel's observation changed the way humanity viewed the heavens, reminding us that the solar system was far larger and more mysterious than anyone had imagined. Over the centuries, scientists have continued to study Uranus with telescopes from Earth and with spacecraft data. The Hubble Space Telescope and large observatories on the ground have revealed more details about the planet's rings, atmosphere, and moons. These modern observations show that Uranus is far from a dull or inactive world. Subtle changes in its cloud patterns, variations in brightness, and movements within its faint rings all hint at a complex and evolving planet. Some astronomers even believe that Uranus's atmosphere could be influenced by seasonal heating, which might cause sudden changes after long periods of calm. Every new observation adds a little more to the story of this distant, sideways spinning world. Deep inside Uranus lies a world of immense pressure and freezing temperatures. The outer atmosphere fades into a vast icy mantle made of water, ammonia, and methane. Farther down, the pressure increases so greatly that atoms are squeezed into strange forms. Some scientists think that deep within the planet, carbon atoms produced from methane could be compressed into diamond crystals, which might then fall like glittering rain toward the center. These diamonds could sink through the icy layers, forming a kind of diamond ocean inside the planet's interior. Beneath that layer, there is likely a small rocky core that makes up only a fraction of the planet's total mass. The structure of Uranus, with its layered ices and compressed materials, makes it very different from the gas giants Jupiter and Saturn. It also makes Uranus and Neptune unique among the planets, forming a special class of ice giants that reveal the diversity of worlds that can form in the universe. The faint rings of Uranus are another of its great mysteries. Unlike the bright, wide rings of Saturn, Uranus's rings are narrow and dark, containing only small amounts of material. Some of them are made of particles only a few centimeters across, while others include larger fragments of rock and ice. The darkness of the rings suggests that their surfaces are coated with radiation-darkened dust or organic compounds that absorb light. These rings may have formed long ago from the debris of shattered moons, or from material that never coalesced into larger bodies. Because of their narrowness, the rings are kept in place by small shepherd moons, whose gravity maintains their sharp edges. Voyager 2 photographed several of these moons during its flyby, showing how they interact with the rings like tiny guardians. Watching these faint, ghostly rings reminds us that even in the cold outer reaches of the solar system, beauty can be found in the most delicate and fragile forms. Uranus continues to challenge and inspire scientists. Although it has been nearly 40 years since Voyager 2's visit, no other spacecraft has returned. Many astronomers hope that one day a new mission will be sent to orbit Uranus, to study its rings, moons, and atmosphere in greater detail. Such a mission could answer many of the lingering questions: why the planet radiates so little heat, how its magnetic field works, what its moons are made of, and how its strange tilt affects its deep interior. Understanding Uranus would also help scientists learn about the countless similar ice giants that are now being discovered around other stars. Many exoplanets found by modern telescopes resemble Uranus and Neptune in size and composition, suggesting that ice giants are common in the universe. By studying our own nearby examples, we can better understand the nature of distant worlds orbiting suns far beyond our own. Even from its remote place in the solar system, Uranus reminds us of how diverse and surprising the planets can be. It is a world of frozen winds and dim blue light, a planet that spins sideways and hides its warmth deep within. Its bluish colour, born from methane gas high in the atmosphere, gives it a calm beauty that contrasts with the violent and stormy nature of its giant neighbours. Yet beneath that calm lies a complex and fascinating world, one shaped by ancient collisions, mysterious chemistry, and time spans so vast that entire human lifetimes pass before it completes a single orbit around the Sun. It is a planet of extremes, cold, tilted, quiet, and distant, yet filled with secrets waiting to be uncovered, and though we have seen it only briefly, Uranus continues to call to us across the darkness, inviting us to return and learn more about the strange sideways planet that glows softly at the edge of our cosmic neighbourhood. Neptune is one of the most distant and mysterious worlds in our solar system, and it is known as an ice giant because of its deep and cold composition. Its appearance is a beautiful and intense deep blue, which makes it stand out among all the other planets. This colour is caused mainly by the presence of methane gas in its atmosphere, which absorbs red light and reflects blue light back into space. The sight of Neptune's swirling blue clouds gives the impression of a frozen ocean floating in the endless darkness of the solar system. It looks calm and still from afar, but beneath that beauty lies a world of violence, coldness, and incredible power. Neptune is the 8th planet from the Sun, far beyond the orbit of Uranus, and it lies in a region where sunlight is weak and the temperature drops to extremely low levels. Even though it is so far from the Sun, Neptune is not a lifeless frozen rock. Instead, it is a world filled with activity, storms, and winds faster than any other planet in the solar system. The winds on Neptune are unimaginably strong, reaching speeds of up to 2,100 km per hour, which is faster than the speed of sound on Earth. No other planet experiences winds this fast. These fierce winds sweep across Neptune's atmosphere, creating gigantic storms that can last for months or even years. The energy driving these winds is one of Neptune's greatest mysteries. Despite receiving little sunlight, the planet produces more heat from its interior than it receives from the Sun. This internal heat rises upward, stirring the gases in the atmosphere and creating powerful jet streams that circle the planet at tremendous speeds. It is this combination of cold, pressure, and heat from within that gives Neptune its wild and unpredictable weather patterns. The atmosphere of Neptune is made mostly of hydrogen and helium, just like Jupiter and Saturn, but it also contains a small amount of methane. This methane plays a very important role in giving Neptune its deep blue colour. In the upper layers of the atmosphere, sunlight interacts with methane, causing red light to be absorbed and blue light to be reflected. But scientists believe there is more to Neptune's colour than just methane, because Uranus also has methane in its atmosphere but appears a lighter blue-green rather than dark blue. This means that something else, perhaps tiny unknown particles or differences in the way light scatters through Neptune's clouds, contributes to its mysterious colour. Beneath the atmosphere, the planet likely has layers of water, ammonia, and methane ices that gradually mix with gases under immense pressure, forming a deep ocean-like mantle that stretches down toward the rocky core. A day on Neptune lasts about 16 hours, which means the planet spins on its axis fairly quickly, completing one full rotation in less than a single Earth day. This fast rotation contributes to its strong winds and violent weather systems. But while Neptune's days are short, its years are unimaginably long. It takes Neptune 165 Earth years to complete a single orbit around the Sun. This means that since its discovery in the year 1846, Neptune has only completed one full orbit around the Sun. To a person standing on Neptune, if that were possible, an entire lifetime could pass before the Sun returned to the same spot in the sky. Neptune has 14 known moons, each with its own unique features and mysteries. The most remarkable of these moons is Triton, which stands out for several reasons. Triton is the largest of Neptune's moons, and it is unlike any other large moon in the solar system. One of the strangest things about Triton is that it orbits Neptune in the opposite direction of the planet's rotation, a movement known as a retrograde orbit. This unusual orbit suggests that Triton did not form alongside Neptune, but was instead captured by the planet's gravity long ago, possibly from a region known as the Kuiper Belt, a distant area filled with icy bodies at the edge of the solar system. Triton is also one of the coldest objects ever observed, with surface temperatures so low that nitrogen freezes into solid ice. Yet despite being so cold, it shows surprising signs of activity. When the Voyager 2 spacecraft flew past Neptune in the year 1989, it discovered that Triton has active geysers that shoot plumes of nitrogen gas several kilometers high into space. These geysers suggest that beneath Triton's icy surface, there might be warmth from the Moon's interior, possibly caused by tidal forces created as it orbits Neptune. The presence of these geysers means that even in such distant and freezing places, energy and movement still exist, hinting at the possibility of chemical reactions or even subsurface oceans far beneath the ice. Voyager 2's flyby of Neptune and Triton in 1989 remains one of humanity's most remarkable moments in space exploration. It was the first and only spacecraft to visit Neptune, and the images and data it sent back changed our understanding of the outer solar system forever. As it passed by Neptune, Voyager 2 captured stunning photographs of the planet's deep blue atmosphere, its storms, and its faint rings. Before this mission, scientists were not even sure Neptune had rings, but the spacecraft revealed several thin, faint rings circling the planet, made up of small particles of ice and rock. These rings are not as bright or massive as Saturn's, but they are important clues about how Neptune and its moons interact. The discovery of Neptune's rings was confirmed during Voyager 2's flyby. These rings are believed to be made up of dark material, possibly coated with organic compounds that give them a dim, reddish colour. They are incomplete in some areas, forming clumps and arcs rather than smooth, even bands. Scientists think the gravity of Neptune's small moons helps shape and stabilise these rings, keeping the particles from spreading out evenly. Though faint and hard to detect from Earth, these rings show that even at the edge of the solar system, complex systems of dust and ice continue to move and evolve. Neptune's discovery itself is one of the most fascinating stories in the history of astronomy. It was not found by accident or direct observation, but through the power of mathematics. In the early 19th century, astronomers noticed that Uranus, the planet beyond Saturn, was not moving exactly as predicted by Newton's laws of gravity. It seemed to be slightly tugged off course, as if an unseen planet was pulling on it with its gravity. Two mathematicians, one in France named Urbain Le Verrier and one in England named John Couch Adams, both independently calculated where this mysterious planet should be. Their predictions pointed to almost the same region of the sky. In September of the year 1846, a German astronomer named Johann Galle used a telescope at the Berlin Observatory and found Neptune exactly where Le Verrier had predicted. This was an incredible triumph for science, showing that mathematics could reveal a planet's existence before anyone had seen it. Neptune thus became the first planet to be discovered through calculation rather than observation, a milestone that changed astronomy forever. Since that time, Neptune has continued to intrigue scientists and space enthusiasts. Even though it is so far away, researchers have used powerful telescopes to study its atmosphere, its storms, and its changing patterns of light. One of the most famous features ever seen on Neptune was a giant storm called the Great Dark Spot, which was first observed by Voyager 2 in 1989. This dark storm, about the size of Earth, was a swirling vortex of winds moving at incredible speeds. Strangely, when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot had disappeared, replaced by other smaller storms. This shows that Neptune's atmosphere changes constantly, with new storms forming and fading in a matter of years. Beneath its swirling clouds and fierce storms lies a planet made mostly of elements and compounds that are frozen or compressed under immense pressure. Unlike the gas giants Jupiter and Saturn, which are mostly made of hydrogen and helium, Neptune and Uranus are called ice giants because they contain much higher amounts of substances like water, ammonia, and methane. Deep inside Neptune, these substances are not solid in the way ice is on Earth, but form a hot, slushy fluid under pressure hundreds of thousands of times greater than Earth's atmosphere. This layer surrounds a small rocky core that might be about 1.5 times the size of Earth. The total mass of Neptune is about 17 times greater than Earth's, making it one of the heaviest planets, even though it is smaller than Jupiter and Saturn. One of the most puzzling aspects of Neptune is how it generates so much internal heat. Even though it receives only about 1/900th of the sunlight that Earth gets, Neptune radiates more than twice the energy it receives from the Sun. Scientists believe this extra heat comes from leftover energy from the planet's formation, or from the slow compression of materials inside the planet. This internal heat helps drive the extreme weather and powerful winds that race through Neptune's atmosphere. As for its magnetic field, Neptune's is tilted at an odd angle, much like that of Uranus. Instead of being aligned closely with the planet's rotation axis like Earth's, Neptune's magnetic field is tilted by nearly 50 degrees and offset from the planet's centre. This creates a strange and uneven magnetic environment that varies across the planet. The cause of this unusual tilt may be the movement of electrically conductive water and ammonia in Neptune's interior, forming a magnetic field that behaves differently from the one generated by Earth's molten iron core. Neptune's distance from the Sun makes it one of the coldest planets in the solar system. Temperatures in its upper atmosphere drop to around -214 degrees Celsius, colder than any place on Earth could ever be. Yet deep inside the planet, temperatures rise dramatically, reaching thousands of degrees near the core due to the immense pressure. This contrast between cold outer layers and hot inner regions gives Neptune a dynamic and restless character, with gases constantly moving and mixing between layers. The faint rings discovered by Voyager 2 also reveal the delicate balance of forces at work around Neptune. The rings have been named after people who played key roles in studying the planet, such as Gall, Leverrier, and Adams. Some of these rings are narrow and contain bright arcs, which are believed to be kept in place by the gravitational pull of small nearby moons. These moons, known as shepherd moons, act like cosmic guardians, preventing the ring material from spreading out. The whole system is fragile and ever-changing, with dust and particles being constantly added or removed by the planet's gravity and by collisions between small bodies. Even from more than 4.5 billion kilometers away, Neptune still affects the rest of the solar system. Its gravity shapes the orbits of many icy bodies in the distant Kuiper belt, and it may even have influenced the early formation of the solar system itself. Some astronomers believe that Neptune's movement through space billions of years ago helped scatter and rearrange small icy objects, shaping the outer regions beyond its orbit. From Earth, Neptune appears as a tiny blue dot, even through large telescopes. But behind that faint light is a world full of wonder and mystery. The Voyager 2 mission gave us only a brief glimpse of it, lasting just a few hours, yet those moments revealed an entire world of storms, ice, and beauty. Since then, telescopes like Hubble and more recently the James Webb Space Telescope have continued to observe Neptune, capturing its changing weather and helping scientists learn more about its composition and its moons. These observations show that Neptune is not a still or frozen world, but an active, living system with continuous movement and transformation. Though it lies at the far edge of the solar system, Neptune remains a source of fascination. Every new observation adds to the story of this deep blue world, showing that even in the cold darkness beyond Uranus, the universe still holds places of great activity and beauty. Its discovery in 1846 marked a triumph of human curiosity and intellect, and the Voyager 2 flyby in 1989 opened the door to a realm that few had ever imagined. With its powerful winds, faint rings, and icy moons, Neptune stands as a world of contrasts, brilliant and dark, cold yet dynamic, distant yet full of motion, and it continues to remind humanity how vast, mysterious, and alive our solar system truly is.